Good morning, everyone. Welcome to today's ACE Medics GCSE physics session, where we will be looking at waves. So thank you all for joining me on a Sunday morning. So if you've not met me before, I think a lot of you have come to these classes. My name is Roshni, and I'm currently a doctor working in London, and I will be running today's session. So what are we going to be talking about? So we will be covering the whole chapter of waves. So we'll be looking at waves in air, fluids, and solids. We'll then be talking about sound waves, and then we'll be talking about electromagnetic waves, and a little bit about lenses and visible light and radiation as well. Okay, so as always, if you've not covered this yet, or you missed out on it at school, or it's been a while, don't worry, we'll start from the basics right up until sharpening your exam technique and being confident to answer harder questions. Okay, so this is just an outline of what today will look like. You will get a break every 45 minutes for 15 minutes or so, and we will break for lunch at 12 o'clock. So during the session, as always, if you have any questions, please just ask me straight away and I will answer them as soon as I can. Please don't just sit there and, leave your computer on. Do try and participate. That is how you'll make the most of these sessions. We will be doing Kahoot quizzes as always, and we've got 4 today. So if any of you can come first in all 4 of them, you can join us for free in our next class. And we have got our top tips. We've got a few of these today, which have got definitions that really you should be remembering that are key take-home messages. Okay, great. So let's just get straight into it. Okay, so when we talk about waves, what do you guys understand? So what do you understand by the term wave? What does it mean to you? Just put your answers in the chat. So some really interesting answers: oscillations, ocean waves, movement of energy. Excellent. So now waves are a bit of an abstract term. So whenever you think of waves, you might think of the ocean, you might think of sound waves, of a slinky spring. But in general, the way that what defines something as a wave is a transfer in energy. Okay, whenever a wave takes place, essentially, if this is my wave, there is a movement of energy from one place to another. Okay, so with a wave, a very unique property is that the substance doesn't actually move, it is just energy that is being carried across in a wave. Okay, that is basically what a wave is. It is a transfer in energy. Now, broadly speaking, okay, there are 2 main types of waves that we have. All waves can be divided up into 2 types. Can anyone tell me what those 2 types of waves are? Fantastic, well done guys. So you are all awake on this Sunday morning. So waves can either be described as longitudinal, okay, or they can be described as transverse. When I was doing physics, I always struggled to remember the difference. So I'm going to show you guys a very nice animation that really explains it. So we've got 2 types of waves, transverse and longitudinal. Now, a transverse wave is one in which the vibration causing the wave is at right angles to the direction of energy transfer. Okay, so you might think, what does that mean? So if we take a slinky spring, which I'm sure you guys have all had or you've seen before, now whatever happens, whenever you've got this slinky spring, the movement of energy is always from here to here. Okay, the energy is always going this way, and you can see that direction of energy transfer. Now, if the wave is transverse, actually what will happen is that the waves will go up and down like this. Can you see that it's going up and then down, up and then down? So this movement is at right angles to the direction of energy transfer. okay, because this is what we describe as a right angle, okay? So with a transverse wave, it is going up and down. So as I said, a slinky spring shows a transverse wave. One end of the slinky is stationary. What do we mean by stationary? Not moving, exactly. Stationary means it is just fixed in position, it is just there. So you might remember if you hold the slinky spring and your friend holds it on the other side, okay, one end of it, you just hold it still. The other end, okay, you just move it from side to side. So you just wiggle it a little bit up and down. And then what happens is that a series of pulses moves down the slinky, sending energy from one end to the other. The energy will always go in this way, okay? It will go from point 1 to point 2. Now, none of the material in the slinky has moved permanently, okay? So obviously the slinky is still the same, isn't it? It hasn't been stretched or pulled. You haven't moved it anywhere. Your hand is still here and here. And this is basically the property of a wave, because waves will transfer energy, okay, but the material is never transferred, okay? There is no movement in the material. So in this example, there's no movement in the slinky spring. It's just like with waves in the ocean. The water doesn't go anywhere, but when we have waves, there is energy moving back and forth. Okay, so can anyone tell me some examples of transverse waves? There are two main examples which you guys need to know about. So a lot of you guys are saying sound waves. That is actually the opposite. That is not an example of a transverse wave. The two main examples, so there is a clue over here. Our main examples of transverse waves are water waves and light waves. Okay, so water as in like the ocean, and light waves from the sun. Okay, these are two examples of transverse. Now, the way that you can remember that is that because basically with the ocean, you know that the water is sort of moving up and down, and that is just like the movement that occurs in a transverse wave. So energy is carried outwards by the wave, but water does not pile up at the edge of the pond. Okay, so whenever you go to the lake or to the ocean, you will see that yes, there are waves going up and down, but it's not like all the water gets pushed to one end and it collects in one area, because that is not what a wave does. It only transfers energy. It doesn't actually transfer the material. Okay, so just try and remember that, guys. So water and light are both transverse waves. Okay, we've then got our second type of wave, which you all correctly identified, which is a longitudinal wave. Now, a longitudinal wave is one in which the vibration causing the wave is parallel to the direction of energy transfer. So again, we've got our slinky. Okay, one person holds it here and one person holds it here. Now, as always, the energy is always going this way. Okay, the energy is only moving in one direction. However, the longitudinal waves are running parallel to that. So what do we mean by that? Well, what we mean is that, can you see how some bits are squished and some bits are wider? Because basically what is happening is these waves are moving backwards and forwards, okay? So if you imagine the slinky's being pushed here and then it's moving out and being pushed in here and moving out and so forth. So the longitudinal waves are essentially just going this way. They're going backwards and forwards. Okay, that was in contrast to my transverse waves, which were going up and down. Now, we've got these bits labeled as R and C. Does anyone know what these are called? Great. So when the slinky spring is squished together, okay, so it looks squished, doesn't it? Now, a more fancier word for that is compression. Okay, we compress it together. So these bits where it's very narrowly, tightly coiled, we call that compressions. Okay, the areas where it's actually pulled apart, okay, and it's relaxed, okay, the R doesn't stand for relaxed, it actually stands for rarefactions. And these rarefactions just basically means bits where it is spread out. So longitudinal waves are basically comprised of compressions and rarefactions, which are just causing the wave to be causing the energy to move forward, but the wave is moving backwards and forwards. Okay, we're only going in this direction. And you can see that everywhere on here. So as I said, in a longitudinal wave, energy is transmitted along the slinky by pulling and by pushing. If you imagine you hold it here and your friend holds it here, you're both literally just moving it back and forth, allowing it to be pushed here and pulled apart. This makes the slinky vibrate backwards and forwards. And this is in parallel to the direction of energy transfer, okay? Because you know that if this is a line here, a parallel line will be this one, right? It will be right next to it, will never touch it. So you can see that here, this is your direction of energy transfer, and here is the movement going back and forth. They're in parallel. And the coils are pushed together in some places. These bits are squeezed, which are our compressions, and in other places they are pulled apart, okay, and they are a bit relaxed. Those are our rarefactions. And as we said, this is only the movement of energy. None of the material of the slinky is being moved permanently. You're still holding it from here and here. We're just transmitting energy with a wave. Oh yeah, so hopefully you guys didn't see that. Can anyone give me an example of a longitudinal wave? Some of you said this for transverse. Fantastic. I'll give you guys that one. So sound is an example of a longitudinal wave. So next time you've got your AirPods in or you're listening to music, that sound that you can hear, okay, is an example of a longitudinal wave. So you can see that here, this is a sound system, and this is a person's ear. So you can see that there are some bits which are squished and some bits which are far apart. But as you guys also said, when you if you have a guitar and you just pluck at the strings, basically what is happening when you start to pull those strings is just moving the energy back and forth, and that vibration is what makes the sound. And we can see transverse waves are over here, and we said some examples of them were light and the waves in the ocean or the water. Okay, so this is just a diagram which I wanted to put in so that you guys could clearly understand what I'm talking about with transverse and longitudinal waves. So as you can see here in the transverse wave, okay, we are literally just going up and then down, right? With our longitudinal wave, we are going back and forth like this. Okay, both of these are transmitting energy, and these are the only two types of wave that exist. So obviously there are loads of waves in the electromagnetic spectrum, but these are types of waves. So wave energy can only be moving up and down, or it can move back and forth. There is no other option. Okay, so does anyone have any questions on transverse or longitudinal? Are you guys okay? Fantastic. Okay, so we will move on now. Okay, so we can describe waves by using some terminology. So what I want you guys to do is, if you've got a piece of paper, I want you to draw this along with me so that you've got a very clear understanding of what I'm talking about. Okay. This is a wave, okay? This is how we always denote waves. And it's really important to have a clear understanding of this because it comes up in loads of equation questions and all sorts. Okay, so this is my wave. Now, there are several things which I can label on here. You might think, what is the significance? So does anyone know, so the wave is going down and then it's going up. Okay, does anyone know what I would call this bit here where it dips? So I'm just going to put up a poll and you guys can vote what you think this dip in the wave is. Okay, so you guys are all very clued on, fantastic. So this is what we call a trough, okay? So a trough is just a fancy word for basically a dip, okay? All things have ups and downs and so do waves, okay? So this is a trough on the wave. Okay, now if this is a trough, this is the high point of the wave, okay, where the wave is at its peak. What do we call this? I think I just gave it away. Excellent. So the highest point on the wave will always be called the peak. Okay, this bit here is my peak, and you guys can label that on your diagram as well. Okay, now this bit here is my baseline, okay, and there is some distance from the baseline. So this is just like 0, the base, okay. The distance from the baseline to the top of the peak, does anyone know what this is called? And we can also say it's the same here. So it's the distance from the top till the bottom of the peak. Excellent. So this causes some confusion, but this is called our amplitude. Okay, so this bit over here will be labeled as the amplitude. And the strict definition of the amplitude I will show you guys is the distance from a peak to the middle or from a trough to the middle. Okay, that is your amplitude. And amplitude is basically like, it determines how loud the sound is. So if you put the volume up on your AirPods, on your music, basically that means that you're increasing the amplitude, and this will be bigger to get a bigger sound. Okay, we will talk more about that now. The next bit is, what about when we go from, this is the bottom of the peak, right? And if I take this and I take one distance of the whole wave, and I go from here, from one trough to another, what do I call that? Okay, a few mixed answers. So well done for those of you that said wavelength. That is the correct answer there. Okay, so this here is my wavelength, and wavelength is in the name. It is basically the length of the wave. Okay, so because you have to start from the same point. So if this is the dip, it goes all the way up and it goes till here. There is another place which I can label the wavelength on here. So if I were to start at this top bit and I were to go all the way around until it goes to the top again, I can also describe this distance as a wavelength. Okay, so this is my wavelength over here. So well done, guys. So just a few key terms as we talked about. So waves are described by the terms amplitude, okay, which we denote as A. Wavelength, does anyone know what this letter is? Great, yeah, this is a Greek letter known as lambda. Yeah, it's just pronounced lambda, and it looks like a bit like a cross. And the frequency, okay, which we described as F. Oh, so we haven't talked about frequency yet. We will talk about that, and we will talk about period as well. You cannot label frequency and period on this graph. So as I said, lambda is the symbol for wavelength and is a Greek letter pronounced lambda. So this is a diagram that we have just drawn together, and you can have that for your reference. Okay, so as we said, the amplitude is the distance from a peak to the middle or from a trough to the middle. Okay, that's the amplitude. It's from here till here or from here till here. The wavelength is the distance between two peaks or two troughs, i.e. from here to here or from here to here. And the frequency is measured in hertz. Okay, so a frequency of 1 hertz means a source is producing 1 wave per second. So we will talk about the equation that connects the wave to frequency and sound. So if, for example, a student using a slinky moves his hand from side to side and back twice each second, okay, that basically means that he produces 2 complete waves each second. So we say it is 2 hertz, okay? So when we talk about hertz, it basically means waves each second. So if in 1 second you move your slinky really fast and you generate 10 waves in 1 second, basically your frequency will be 10 hertz. Okay, and frequency, as we will see, is very much related to pitch. So if something sounds very high pitched, then it tends to have a higher frequency because the waves are closer together. Okay, a few more definitions. Now, we describe the period, which is known as T. It's called T because T stands for time, and that's how you can remember it. So the period of the wave is the time taken to produce 1 wave. So how long does it take you to push that slinky so that you get a wave? Okay, and the frequency and time period of a wave are linked by an equation. Does anyone know what the equation is? So T, okay, which is my period, is 1 over frequency. Okay, excellent. A lot of you have got that, so well done. I'm really impressed. So period is in seconds, okay, and frequency is in hertz. Now, you might think, how do I memorize this? But this is actually something that you can understand. So basically, we're just saying, how long does it take you to produce 1 wave? Your frequency is the number of waves per second. So if you divide that by 1, it will give you the time of how long it took you to make 1. So that's how it works. So period is in seconds and frequency is always in hertz. Okay, so let's just have a go at a question. So we'll do this together. So calculate the period of a wave with a frequency of 10 hertz. So have a go. You can use your calculator or you can actually do it in your head. So whenever we do these questions, just so that you can get all the marks, just make sure you write out your working out, even if it's really obvious. So we just write out, we know T is equal to 1 over F. So therefore, I'm trying to calculate T, right? So it will be 1 over 10, because that's my frequency, which is equal to 0.1. Always give your units, guys. Don't give me any answers without units, because you will lose the mark. So period is in seconds, so we say 0.1 seconds. Okay, so that is my answer. Okay, well done, guys. Great. Okay, so let's move on. This equation is quite basic, and there is the more complex equation that you guys need to know about is coming up next. So, because a lot of the time we don't just want to calculate the period, we want to calculate the wave speed. Okay, so because we're not just always looking at slinkies, sometimes we're looking at the ocean, sound waves, and much bigger things. And we want to know how quickly is that wave moving. So what does wave speed mean? Wave speed is the speed at which energy is transferred or the wave moves through the medium. Okay, does anyone know what I mean by medium? Fantastic, the surrounding or the material. Great, so the medium is just what we're trying to go through. Okay, so that could be the ocean. If it's a sound wave, you know, it could be the air. Even if it's a light wave, is trying to go through the air, right? It's just what it's trying to get through to transfer the wave, okay? Because remember, the wave never transfers material, it is just moving energy. So we have our equation, V equals F lambda. Okay, so just walk me through this one. What do you think V stands for? Excellent, this is wave speed, okay, is equal to, what would F be? That should be easier. Frequency multiplied by my lambda, which we said was wavelength. Great. Okay, and this is an equation that this is one that I hope that you guys can remember after today if you don't remember anything else. Okay, now wave speed is equal to frequency multiplied by my wavelength. Okay, because frequency is how often I'm getting the wave, and wavelength is how long is that wave. So obviously that will tell me my speed, right? So I'll know how quickly is that wave moving and how long is each wave. That will give me the speed. The units that we measure it in is meters per second. Okay, so sometimes you might get a question in centimeters, they might give it to you in minutes if they're trying to be really mean. So you have to always remember it's in meters per second, and then you have to convert it. Okay, what is my unit for frequency? If this is meters per second, what do we always measure frequency in? Fantastic. Frequency is measured in hertz. Great. And what is the wavelength measured in? So yeah, wavelength, so the sign for wavelength is lambda, but that is not a unit, okay? That is just how we denote wavelength. The unit for measuring the wavelength will be in meters, okay? Because remember, if this is in meters per second, obviously this has to be meters, it can't be centimeters, right? So wave speed is in meters per second, frequency is in hertz, and wavelength is in meters. Okay, so we've got the basics. Let's have a go at a question, and I've put this here to help us out. So sound travels at a speed of 330 meters per second in air. Okay, so air is what we call the medium. Calculate the wavelength of a sound wave with a frequency of 660 hertz. So have a go at that one. Okay, so a few mixed answers. So guys, give me your units as well, please. Okay, let's try and go through this because literally everyone has said something different. So if you get a confusing question, just see what are they asking you to work out. They're asking me to work out wavelength, okay? So basically I'm trying to work out wavelength. If I need to work out wavelength, I need to rearrange this equation, don't I? Because you have to make it wavelength equals. So if I have to rearrange this, I will say wavelength equals wave speed over frequency. Okay, because I'm trying to solve it for wavelength. Now my wave speed is in meters per second, okay, and they've told me the wave speed here is 330. So I can say 330 divided by the frequency, which they have given me, is 660 hertz. Okay, and if you plug that into your calculator, you should get 0.5. or you can do mental arithmetic. Can you see it's a half? You get 0.5, and remember we said wavelength is in meters. So my correct answer is 0.5 meters. Does anyone have any questions on that? Well done if you got it right. This is a harder question. It's not straightforward because it's not asking for the wave speed. You have to rearrange the equation. Okay, let us try another one if you were not successful with that one. So a stone is thrown into a pond and waves spread outwards. Okay, the waves travel with a speed of 0.4 meters per second and their wavelength is 8 centimeters. Calculate the frequency of the waves. Okay, this question is a little bit unfair because you need to look at the units as well. Okay, I will start working this one out. So I'm being asked to calculate the frequency of the waves, right? I'm trying to work this one out. So again, I need to rearrange my equation. So I can say frequency is equal to wave speed over my wavelength. Now, wave speed is in meters per second, and they've given it to me. It is 0.4 meters per second. Wavelength is always measured in meters. They've given it to me in centimeters, okay? So that is where you need to pay attention. So I know that 100 centimeters is equal to 1 meter. So therefore, 8 centimeters will be 0.08 meters. Yeah, hopefully you guys don't have any trouble with that. You just divide it by 100. So I've got 0.08 meters. And if I plug that into my calculator, I believe the answer is 5. Okay, and then we don't stop there. We put our units, which is in hertz. So it would be 5 hertz. Fantastic. Most of you got that one. So that is excellent. Okay, great. So keep this equation in mind. It will come up in the quiz. So let's talk, we're just going to move on to talking a little bit more about how can we actually measure these wave speeds. So with that equation, we can actually measure it in a laboratory. I don't know if you guys have had any chance to do any of these experiments in school, but basically what you can do is you can get a tuning fork, which is that metal fork that, you know, when you hit on something, it vibrates and it makes that really annoying sound. So basically you can take a tuning fork and you hit it on like a table. Okay, so let's just imagine you've hit it on a table and then it vibrates, and basically the vibrations that it makes causes some ripples in the water. You will see that the water moves up and down, and a few of you have done this in school, so that's cool. So you can see that the water, you will basically see ripple movements as the vibrations will travel. Okay, and you might want to calculate, well, what is the speed of this wave? Like, how quickly is this moving? So what you can do is you just use the equation speed is equal to distance over time, because this we're just doing like as a casual experiment in school. So you can just measure how far was the tuning fork from your water and how long did it take until you saw those ripples. So you just do distance over time. Okay, now the problem with measuring the speed of sound in air is that it travels really quickly, because obviously as soon as you hit it, it makes that sound and the vibrations move. So it's quite hard to measure that with the naked eye and to see the ripples, because it's literally like milliseconds. So we must find a way to measure short times accurately in the lab. So we've got a bit more of a fancier experiment, which you guys probably haven't done. So what you can do is you can get a loudspeaker. Okay, this is my loudspeaker over here, and you can connect it to a signal generator. So what a signal generator does is it basically produces sound. It just pulses out loads of sound. It's not like music or anything, it's just sound waves, like quite loud, annoying sounds. You then put 2 microphones near the loudspeaker. So you put one here and you put one here, but you just separate them. You don't put them next to each other. And each microphone is connected to an input of a dual beam oscilloscope. Don't worry about this fancy term. Basically, an oscilloscope it just shows you the movements of the sound waves. So you can see that here. We'll just create these traces whenever the sound waves pick up. Oscillo comes from oscillates, okay, which means moves back and forth. That's how I remember it. So as soon as it picks up the sound waves, it will just move up and down. And the oscilloscope can measure the time difference between the sound reaching microphone A and microphone B. So this is just a way of doing it in a lab. You don't really need to know too much about this, but just that they used what we call an oscilloscope. Okay, and what if you are outside? So let's say you guys are outside and you want to measure how loud is your voice traveling or any kind of sound. Does anyone have any idea of how you could do that? Because they do like to ask about experiments and exams, so it's good if we start having a think. So yeah, this image gives it away. So basically what you can do is, if you've got a very tall building, you will know that sometimes if you shout out loud, it can echo and the sound can come back. So when you're outside, the echoes from a tall building can be used to measure the speed of sound in air. And basically what you can do is, like, you and your friend can go and stand like far away from the building, and you can just make like a really loud racket and start banging some blocks of wood together. And what you can do is you can then, you will hear that there is an echo because there is a tall building, so the sound waves will basically bounce back, and you can measure the time of how long it took for you to hear the echo. So each time you hear an echo, you bang the blocks together again, and so one of you can be banging the blocks, and another person can use a stopwatch to time how long it took. So you can see each time you can say how long does it take for the sound to travel back. Okay, so I think I just want to do a couple of exam questions before we do our quiz. So the diagram shows a longitudinal wave being produced in a stretched spring. Use the bold words from the diagram to complete the following sentence. Put only one word in each space. So a longitudinal wave is one in which what do you think? And guys, it says just whenever we do exam questions, please just read the question, because it's saying use the bold words from the diagram. So do not start making up your own words here. Okay, you will get 0 anyway, and you'll be wasting your time trying to think about it. It's asking you to use these words. So any of these, you can just put them in. Okay, so this is actually quite a tricky question. So a longitudinal wave is one in which the correct answer here is oscillation. Remember, we said oscillation is that movement back and forth. Causing the wave is parallel to the direction of energy transfer. Okay, so do you guys remember that we said that with a longitudinal wave, someone holds a spring here and the spring is here. The energy is always moving this way, but the wave is going back and forth. The oscillations, i.e. that movement, is back and forth, and it is always parallel. These will never touch. We contrast that to our transverse waves, which we said go up and down. and they occur at right angles to the direction of energy transfer, okay? So that is what separates them. These are parallel. So just to make that very clear, longitudinal is parallel and transverse is at right angles, or we say it is perpendicular. Okay, that is another word for right angle. Okay, name the type of energy that is transferred by longitudinal waves. So what was the main example we said longitudinal waves carry? Was it excellent, it is sound. Okay, that is the main one that longitudinal waves carry. All right, fantastic, guys. So we'll just pause there and do a quick quiz on what we have covered so far. Okay, I think we'll get started. Fantastic, that is true. So either wave is transverse or it's longitudinal. Fantastic. So they will all have a wavelength, frequency, amplitude, and speed. Rest point is not a thing, okay? That's why all of these are wrong. Fantastic. They move up and down. Excellent. So longitudinal waves, they move back and forth, okay? Those are those oscillations. Excellent. So sound waves are the main examples of longitudinal waves. Okay, hopefully no one should get this one wrong. Excellent. Sound waves are longitudinal. Excellent. So all waves, they transfer energy only. They don't transfer material. Okay, this question is quite hard. Okay, so with this one, they've given us the wavelength, and they haven't given us the frequency. But basically, you can work out the frequency by seeing how many times does the wave appear in one go, and basically you just count it from one trough to another. So this is one wave, two waves, and three waves. Okay, so you would divide it by 3, and that would give you 0.53. All right, fantastic, guys. Well done. So we're just going to stop there and go for a break till 11 o'clock, and we will then continue with our next session. If you've got any questions, please just leave it in the chat. Well done, guys. So I'll see you after the break. Hi everyone, welcome back. So I hope you enjoyed your break. We're just going to do a few more exam questions before we move on to the next topic. Okay, so let's have a look at this one. So bats use the reflection of high-pitched sound waves to determine the position of objects. The image below shows a bat and an insect flying in front of the bat. Okay, there's my insect and there is the bat. What determines the pitch of a sound wave? Fantastic. So the correct answer here, which we touched on this briefly, is the frequency. Okay, so if this is my wave, okay, and if all of a sudden the waves start to be much more closer together like this, okay, so here the frequency is much higher, and the more often your waves are, okay, the higher the pitch. Again, this is my wave here. If the waves were to become like this and become really, really big, okay, that would increase the amplitude. Remember, amplitude is the distance from here to here. And if the amplitude is increased, it means the sound is increased. So the sound will be louder, okay? So amplitude is to do with this, how loud or how quiet the sound is, and frequency will determine whether it is a high pitch or a lower pitch. Okay, state the name given to reflected sound waves. So this came up when we talked about when you are outside your school, outside a tall building. Excellent. So when a sound wave gets reflected back, it's known as an echo. Okay, the bat emits a sound wave with a frequency of 25 kilohertz and a wavelength of 0.0136 meters. Calculate the speed of this sound wave. And just be really careful with the units here. Excellent. So we know that our equation, okay, is wave speed is equal to frequency multiplied by my wavelength. Now they are asking us to work out the speed, so we don't need to rearrange any equation over here. Now, frequency, we measure in hertz. Wavelength, we measure in meters. The frequency given to me here is in kilohertz, okay? So I need to convert it into hertz. Obviously, if this is kilo, that means it's 1,000 times 1,000. So I have to times 25 by 1,000. Okay, so that would be 25,000 hertz. Because basically 1 kilohertz is equal to 1,000 hertz. Okay, it's just like, I always try and make it simple. It's like how you say, you know, that 1 kilogram is equal to 1,000 grams. It's the same thing with hertz as well. So 25,000 hertz multiplied by my wavelength, which is 0.0136. Okay, and if you multiply these together, you should get 340, and they've given you the units, 340 meters per second. Okay, does anyone have any questions on that one? A bit tricky because of the kilohertz. Great, yep. So these are the answers here. So echo and 340. So you would get 1 mark for trying to sub it incorrectly. But yeah, if you got the incorrect value, yeah, you would just get 1 mark. And we've got a question which says, does it always need to be converted? Yes, you have to convert it into the correct values, otherwise you will get the question wrong. So we always measure frequency in hertz, wavelength in meters, and wave speed in meters per second. You always have to use these regardless of what they give you. You must convert it, otherwise the equation, you will get it wrong. Okay, so we're going to move on to talking a little bit about reflection now, and reflection of light. So as I'm sure you guys know, whenever you look in the mirror, you can see your reflection. The reason that you can see your reflection is purely because light is being reflected. Okay, and any mirror which is just a flat surface, like the one that you may look at, or if you go into a dressing room or something, this is called a plane mirror. Okay, plane means because it is flat or lying in the surface of a 2D area. Okay. Now, basically, what we can do is we can investigate how light is being reflected using what we call a ray box. A ray box is just something which emits the light ray, and a plane mirror, which is just a flat mirror. And basically what this ray box does is it produces a narrow beam of light. Okay, so it's just a box which emits light energy, and we call this a ray. Okay, so I want you guys to just draw this along with me. So if we imagine this surface is my mirror, okay? So just imagine that you have put a mirror over here. Okay, we've then got basically this box here is called my ray box. And what this thing does is it emits light rays, okay? So what will happen is if, for example, it's just like, if you imagine it's like a torch, okay? Let's say you get a torch and you put it in front of your mirror. What will happen is that it will emit a light ray, which will just hit the mirror like this, okay? Now, what happens with a mirror is mirrors always reflect the light. So the ray will come in and it will get reflected right back out. So we can show the movement of the light ray. So the light is going this way, okay? It's going to hit the mirror, and then the mirror reflects it, and it reflects it right out. So we have specific terms to describe each of these rays. Does anyone know what this ray is called, the one that hits the mirror? Exactly, so this is my incident ray, okay? This is where the incident happens, and this is where it starts off. Does anyone know what this ray is called, the one that gets bounced back? Great. This here is called my reflected ray. Okay, so you can just imagine, like, if, for example, this is your eye over here, this is what you would look at, and this is what you would see. So this is basically why you can see yourself in the mirror. And because whenever it's light outside, the light hits the mirror and it bounces back in your eye. This is why when it's dark and you look in the mirror, you can't see anything because it's dark and there's no light. Okay, now the way that the light ray hits it, it's not random, okay? It doesn't just hit it at any angle, but if this was to be the middle, we call this the normal. The normal is just basically the normal thing, and it sits in the middle. So the angle at which it hits it, which would be called the angle of incidence, okay, will be equal to the angle of reflection over here. Okay, so this is the way in which the light ray works. So the way that it hits it at the incident is equal to the way it was given off, okay? Because if you imagine, otherwise your mirror would be quite messed up. Like if instead of it hitting it over here, let's say the light just went over here, okay, then you wouldn't be able to see anything because your eye is over here. So this is why it hits it at equal incidence and equal reflection. It doesn't just bounce off in any direction. The way it hits it is equal. Okay, so you can just see that very nicely over here. So your angle of incidence is equal to the angle of the reflection, of the reflected ray. Okay, so just a few key points on that. So the line drawn at 90 degrees to the surface is called our normal. Okay, that was this here. We just call this the normal because this is at a 90-degree angle. Okay, this is 90 degrees on both sides. The angle between the incident ray and the normal is the angle of incidence. Okay, that is this angle here. And the angle between the reflected ray and the normal is called the angle of reflection. Okay, and that is this one over here. So just try and remember these keywords. So normal, angle of incidence, and angle of reflection. Okay, we can see that all over here. And as I said, whenever light is reflected, so any kind of light, whether that is from the sun or you use a torch or any artificial light, this rule will always be obeyed, okay? So that your angle of your incidence will always equal your angle of reflection. Okay, so this is before reflection. This is just in another diagram. The angle of incidence here, if this is 45 degrees, this will also be 45 degrees. Okay, and this rule of refraction is true for all types of waves, okay, even sound waves and even water waves, okay? So this is why whenever you look, if you're by the lake or by the river, you can see your reflection sometimes in the water, and that is because the way that the light hits the water, the angle of incidence is equal to the angle of reflection, so you can sometimes see yourself. Okay, and you can see the water waves being reflected off a solid barrier in a ripple tank. So that's just here. So if this is, these are your water waves, and it's just the same thing that it is reflected. Okay, so just looking a little bit more about images in a mirror. Now, we call this a ray diagram. So ray is just the light. Okay, and this is a ray diagram. So the ray diagram shows how an image is formed in a plane mirror. So what you can see is this is your mirror over here. Okay, and this is an object. So let's just say you have got a cup of tea over here. Okay, that's my cup here. So there's an object here, and then obviously what happens is if you've got an object that's in your mirror, you can actually see the object over here, right? When you look in the mirror, the distance is equal. So two rays from the object, the red and the green ray, are reflected by the mirror into an eye. So both of these rays from the object, they hit the mirror, okay, and then they hit the mirror and then they hit the eye. So we just follow this path here. They hit the mirror and then they reflect back. Okay, so angle of incidence is equal to angle of reflection. Obviously, all objects have got more than one ray. They don't just have one light ray. So this is another one, and it hits back into the eye like so. Now, basically, these rays are diverging, and they appear to have come from a point behind the mirror. So diverging means that they are spreading apart. So these are divergent rays. One goes here and one goes here. They are going far away from each other. And the brain interprets the rays as coming from an image behind the mirror. And this is called a virtual image because you know that when you look at an object, okay, if your object was here and you see it over here, you know how this is 3 centimeters away from the mirror, and this is also what appears to be 3 centimeters away. Now, this cup of tea is not actually sitting behind the mirror. This is just a virtual image, and it is purely to do with the reflection of the light rays. And just a little bit more on that. So this image shows it a bit more clearly. So whenever you look at an image in the mirror, the virtual image is always the way up. So if you've got a candle that's near your mirror, you will see the candle looking the right way up. Okay, the candle is never going to be upside down or anything like that, because the virtual image will always be the right way up because of the way that the light rays travel. Now, very interestingly, when you look at yourself in a mirror, if you put your right hand up, you can try this out later. If you put your right hand up, what you will see in the mirror is that actually the left hand is being raised because it is a direct reflection. And the ray diagram shows this. So when you look towards the object, the green ray is on the left, and when you look at the image, the green ray is on the right. So I'll just show you that over here. So what you can see is that here, the green ray is on the left side, okay? But when you look at, when it is reflected in the mirror, it is towards the right. So it is actually further on this side. So can you guys see that? Because here, the green ray's gone here, but in the mirror, it is further out, okay? And that is basically because the mirror swaps over the image. So if you put your left hand up, it looks like the right hand is up, and that is purely because the rays will diverge. Okay, and a plane mirror will always produce an upright virtual image. Okay, it's never going to be upside down. So it may be that the left and right are the opposite, but it will always be the same way up. Okay, so that is looking at a mirror. Okay, now we know that mirrors are very good reflectors of light, because with a mirror, all the light that goes in, it bounces right back out, okay, and you see everything. But not all objects are like this. So, for example, if you take a piece of glass, like if you've got a glass table, sometimes you might be able to see yourself in the glass, okay? And that is not always the case. It depends on the type of glass and how much light there is. But there are lots of objects which you can sort of see yourself, but not fully. So we're going to talk about that now. So a mirror is a really good reflector of light, and nearly all the light that is incident on the mirror is reflected, okay? So if this was a mirror, everything that hits the mirror, it comes right back out. Now, other surfaces, like for example glass, what they do is they can either transmit or absorb the light. Okay, that is, they both mean the same thing. So now let's say, for example, this is my light ray that hits a piece of glass. Now usually you expect all the light will just bounce back and you'll be able to see yourself, but actually with glass it's not the best reflector of light, and some of it will just go through the glass and some of it will go out. So this is why when you look in a piece of glass, you can't really see yourself clearly. You might catch a glimpse of yourself, but the image tends to be quite distorted and it looks quite messed up, which I'm sure you've experienced before. And that is because some of the light is transmitted or it's absorbed by the glass itself. It doesn't push it all back out. So the diagram shows a light ray incident on the surface of a big block of glass. And as you can see, some of the light is reflected off the surface. So yes, we have got some light going out, but some of the light is going through the glass. Okay, and this means that the image won't appear as clear. Okay, and we call this the transmitted ray. So transmission just means it goes through. Okay, like if you transmit a signal, you pass it through. And what happens is that the transmitted ray will change direction. So obviously, instead of just like going back up, it chooses its own direction, whichever way it wants to go through. And this is really common when waves travel from one medium to another, like for example, when it's going from air to glass. And some surfaces will absorb the light, and this is very common in, for example, when you have in your own home, your ceilings, they might be painted white and the walls may be painted bright light, very light colors. And basically what that does is, because these light surfaces, what they tend to do is they tend to absorb the light and they tend to take it in. So because they are taking the light in, that is what makes the room very bright and very well lit. So we use these properties in everyday life as well. So just a few more examples on that. So if you put a black or dark color paint on the wall, the room will be darker. Okay, so what you can see is here, these are three different mediums that we have. Okay, so this is a piece of glass. Okay, and this is like a really dark black object, which you can see like a black wall, and this is a white wall. Okay, now light is going to hit all of these surfaces. So what happens is with the dark object, the dark color paints, they tend to take all of the light in, okay, because dark objects, they are attracted to light, so they take all of the light in. So what that means is that less light is reflected. So that's why your room will tend to be dark. Okay, if you paint it white, okay, the light that hits it just tends to bounce off, so the light is reflected all around the room, and it makes your room more brighter. And then, as I said, with a piece of glass, glass is a very poor transmitter, so it will just take it. It will, sorry, it's a poor reflector, so it will just transmit the light, and the light will go through. And some other examples. So all waves are affected as they travel from one medium to another. Okay, so all of these boxes here, these are known as different mediums, like a dark object, a light object, a piece of glass, a piece of wood, and the wave gets affected. Okay, so either it will be transmitted, or it will be reflected, or it will be absorbed when it travels through a different medium. And some other examples of that are, so sound reflects well off a cliff, and you hear echoes in the mountains. Okay, so that is basically because you are moving from a different medium. So you're going from a cliff to a mountain. Okay, and we use these properties. So for example, modern houses are designed to absorb sound so that we are not disturbed by noisy neighbors. So if you have got obviously thicker walls, they will absorb the sound energy so that the sound doesn't come through. Okay, I just want to do a quick question now. So figure 2 shows a ray of light incident on a semicircular glass block. Complete the ray diagram in figure 2. Draw the ray of light passing through and leaving the glass block, and label the angle of refraction. Okay, so I want you guys to have a go at that. This is 4 marks. So I'll just start working my way through this one. So basically with this type of question, some of it we haven't covered yet, but we'll talk about this. Now, if this was a mirror, Okay, the mirror one we drew very clearly. If it was a mirror, this is my angle of incidence, and this is my angle of reflection. Okay, that would be fine. We said that not all objects are like mirrors, and some are less reflective. So for example, a piece of glass. Okay, so they've given us a piece of glass. Now, with any of this type of diagram, okay, this is 4 marks, so you obviously need to do quite a bit. This is my angle of incidence. We always draw the normal. Okay, you will get 1 mark for drawing this normal. It's usually actually as a dashed line to make it clear. So I'll just make it dashed like so, and you can label it and you can write this is the normal. Okay, the normal is always at 90 degrees to the surface. This is my normal, and this here is my ray of incidence, and this is my angle of incidence. Okay, this is my incident ray. Angle of incidence, or you can write here my incident ray. Okay, now this light ray has hit the glass block. So tell me guys, what is going to happen to most of the light? Is it going to go through the glass or is it going to come out? So just tell me, is it going to go through or back out? Fantastic. Most of it will go through because remember, glass is a poor reflector. Okay, it's not as good as a mirror. Most of it will just take it in. It will not reflect it out. So that's why you won't be able to see yourself. So most of the light will go through, and instead of bouncing out like this, actually what happens is you can draw it however you want, but it goes through it. Okay, you can even draw it like you could draw the angle here or you could draw it here. That doesn't matter. It's just that you show that the majority of it will go through. Okay, so just for our purposes, I'm going to leave mine like that. Okay, now we said that if it is reflected, if some of it is reflected, we call that the angle of reflection. Okay, if it is not being reflected and actually it is being transmitted, we have another fancier word for this angle. Okay, and we call this angle the angle of refraction. Okay, and basically all refraction means is that it is going through and it is not going out. Okay, so most of the light usually gets reflected, but some of it will be refracted, and this will be my angle of refraction. Okay, so that is basically what you would get the 4 marks for. So I wouldn't, because it is saying draw the ray of light passing through, so you don't need to show what is being reflected. That is not where you will get the marks for. The marks will be for drawing the ray of light coming through here and labeling your angle of refraction. So you can see that here. So ray of light refracts towards the normal where it is incident on the glass block. A normal is drawn on where the ray is incident and the angle of refraction is labeled. So just like this, basically what we drew, you'll get a few marks for that. Okay, does anyone have any questions on that? I know these exam questions are, it's quite hard because I know we've covered all the knowledge, but it's still hard to do the exam questions. So this is why we just try and do as many as we can. So we'll just look at the first part of this question. So figure 1 is a wave front diagram showing light traveling through air and into a glass block. Okay, it's going through air and then a glass block. Sorry, that was the answer. So complete figure 1 by drawing wave fronts after they have left the glass block. So remember we said that whenever waves go from one medium to another, it affects them. Okay, so what do you think you guys will draw for this? So basically, this is the wave in air. Okay, this is the wave in glass. Now, basically, waves are just a movement of energy. Okay, light is just moving through this, but we said that whenever we go through a different medium, okay, the waves, they change. So you can see here that the waves are quite spread apart, and when they go through the glass, because of the change in the medium, they tend to be closer together. If I come back out in air, what do you guys think will happen to the waves? Do you think they will be the same as this? Do you think they'll be the same as they were in air, or they will have changed to glass? There will be waves changing direction. Fantastic, they will have changed. So basically what will happen is we've gone from air to glass, and now we've come back out into the air. So what will happen is the waves will just behave as they would in the air. Okay, so that's all this question is trying to tell you. So you just draw them out how they are in the air, because now they've left the glass, so they will go back to how they were in air. So if you just draw them out like this, basically it shows that you're not understanding that we've now changed the medium again, because this looks the same as this. So we've gone from glass, we've gone from air to glass here. So they were widely spaced and now they're close together. But now we've come out into the air again. So they will go back to how they behave in air. So they would be like this. Okay. Then if you were to put like another glass block here, then they would be more squished together. Again, they would come out and be normal. If you were to put something else, like say a piece of wood, okay, they might be even closer together or they might look more different. It's just dependent on the different medium. But if they behave like this in air, as soon as they come out of the glass into the air, they will behave like this again. So you can just see it over here. So this is how it is. So they've just drawn it the same as how it was in the air. So you can just draw 2 or 3, as many as you want, but at least more than one to show the spacing. Okay, guys, so we're just going to do a quick quiz on light rays, sorry, on reflection before we move on to the next little bit. I think we'll get started. Excellent. So when something is being reflected in a mirror, okay, the angle of incidence is equal to the angle of reflection, and that's how this cat you can completely see the cat in the mirror, because the angle at which the light hits is equal to the angle at which the light is reflected. Okay, so this is a little bit of recap from our previous section. So the number of waves passing a point per second is called the frequency. Okay, I will just show that to you guys over here. Where has it gone? So frequency means the number of a source producing one wave per second. Okay, so there is a number of waves passing through a point at each second. So essentially, if 5 waves pass a point every second, that means that the frequency is 5 hertz, okay? So 5 waves pass a point every second, the frequency is 5 hertz, and we said that the period is 1 over frequency. So if my frequency is 5, I do 1 divided by 5, which will give me 0.2. Okay, so 0.2 seconds is the correct answer. Well done. Excellent. So wave speed is equal to frequency in hertz multiplied by wavelength. So it will be 4 multiplied by 2. Okay, I think some of you got 2 because you did frequency divided by wavelength, but remember we multiply them. Okay, what is reflection? Excellent. So all reflection is, in very simple terms, is it is light that hits a surface and comes right back out. Okay, it does not get transmitted, it does not get refracted. Excellent. So in reflection, okay, the angle of incidence, which is this angle here, is measured between the normal, okay, and the incident ray. It's this angle here. The angle of reflection is between the normal and the reflected ray. Okay, tricky question. If light is transmitted, okay, basically what happens is it goes through the object. That is the definition of transmission. It will go through. For example, if light goes through a glass, if it's transmitted, it just goes through it. So which has the longest wavelength? Wave 1, 2, 3, or 4? So the longest wavelength, remember the wavelength is the distance from one peak to another, or one trough to another. So this is the peak here, and then we measure it from this peak here. We can measure it from this trough to this trough. That is the distance of one wave, right? So if we look at that, obviously the further apart it is, the longer the length of the wave, the longer it takes for one whole thing to go through. So that's obviously 3. These ones are all much, much closer together. Excellent. So frequency is the number of waves given in a number of waves produced in a given amount of time. Hertz is the unit that we measure frequency. Okay, so you may know on your radio that you change it to hertz because that is the frequency of it. amazing. So some of you have got full marks, so that is amazing. Fantastic, guys. So we're just going to move on now to, we've covered reflection. What I want to do now is to move on to talking about sound waves. Okay, so we've got a lot of waves coming up. I don't want anyone to get mixed up. We are now talking about sound. So just a quick refresher, what type of wave is a sound wave? Is it longitudinal or is it transverse? Fantastic, it is a longitudinal wave, okay. Now, how do we get sound waves? The only way, you might be wondering, where does sound come from? Well, essentially sound comes when an object is vibrating, okay. Anytime something vibrates, it produces a sound. Now, a very classic example is a tuning fork, which is used to produce a musical note or any kind of loud sound. So what happens? Well, when you use a tuning fork, which I'm sure you guys have done before, as soon as you bang it, okay, what happens is these get hit together or they hit any surface. And the only reason this works is because the prongs, i.e. these are what we call prongs, they vibrate, okay? That is the key point here. The touching of them causes vibration and they produce compressions and rarefactions in the air. So remember, compressions are when it is squeezed. Think of that slinky spring which is squeezed, and rarefactions are when it is relaxed. Okay, and there are gaps between them. And as we said, sound is a longitudinal wave. Now, sound waves, they don't just travel through the air, okay? Tuning fork is obviously a very common example, but sound reaches our bodies, it travels through oceans, it travels through everything. So sound waves can also travel through solids and fluids by setting up vibrations in those media. Media is plural for medium, and medium is what it is going through, like, for example, your body or the ocean. So you can make a glass ring by rubbing a wet finger around its rim, okay? And vibrations in the glass send sound waves into the air, okay? So basically what you do is, if you get a ring and then you put a wet finger and you rub it across, you may hear that there are some sound waves being made from that. Now, basically, how does this work? Well, the only reason that we can hear things is because, as I said, because of vibrations. Okay, now our ears detect sound by converting the vibrations in the air, which are sound waves, into mechanical vibrations in a solid. Okay, and if any of you guys go on to do A-level biology or even medicine at university, you will learn a lot more about the ear, which is a really complex and fascinating organ. But inside of our ears, we've got a whole unique piece which allows us to convert the vibrations from the air and to process it into a sound that makes sense for our brains to understand, okay? Because vibrations don't really mean anything, but our ears can convert it into a way that we can actually say, oh, that's the sound of my mum talking, or that's the sound of my phone ringing, okay? Because of the difference in vibrations. And this is just basically what the ear looks like. So this is the eardrum. Anytime sound hits, any vibrations that hit, it causes the drum to vibrate. Okay, anything that, so even me as I'm talking right now, because you can hear me, your eardrum starts to vibrate. And that vibration just sets off some more pathways inside the ear, and it then converts the sound. So we'll talk a little bit more about that. So the compressions and rarefactions in the air set the eardrum in motion. Okay, you can think of the eardrum as literally a drum. So like a drum that you've had in music, you know, when you bang on it, that is literally what is inside the ear. It is a drum that is absorbing vibrations. Now, as the eardrum vibrates backwards and forwards, okay, it's generating its own movements, and that causes some smaller bones, which are deep inside the inner ear, to vibrate as well. And the vibrating bones are connected to nerves, which are in our brain. okay, and they give us the sensation of the sound, because at the end of the day, these are just vibrations, but our brain is able to interpret it as some meaningful sound. Now, the conversion of sound waves to vibrations in the bones only works over a limited range of frequencies. Okay, so remember, everything is frequency, which is how often we have a wave in a second. So some really high-pitched sounds, okay, we can't actually hear them as humans. Okay, and then there are some very, very low-pitched sounds which we can't hear. Now, what can happen is people who work in areas where there are a lot of loud sounds, like if they work in drilling or like, any building sites, because they're exposed to all of that chaos and that sound all the time, that can affect their ears, and they can probably not hear sounds that we can hear. Or if, for example, you listen to your music, if you've got your AirPods plugged in all the time, it can affect the inner ear, and then some sound frequencies you may not be able to hear later on in life. So yeah, just a word of warning. Okay, so what can we as humans hear? Okay, so the human ear can detect sound over a range of frequencies. Okay, remember, anything in hertz is frequencies. So we can hear stuff from a range of 20 hertz to 20,000 hertz. They do sometimes ask this, so it's good to remember this. So this is a huge range of frequencies, but there are actually some animals that can hear like below this and higher than this. So that's why some animals can hear things that we can't. So, which is quite interesting. So elephants, they can actually hear below 20 hertz. Dogs can hear much higher frequencies than us, and even dolphins and bats. So some things that we can't hear, which might actually be around us in the earth, some animals can hear. And we can just see this chart over here, which is just showing frequency at the bottom. And basically what I want to point out to you is, don't worry about the numbers, but can you see how if something is 20 hertz, that means that the frequency is lower. So can you just see it's like one wave like this, it's really slow. If you go all the way to 150 kilohertz, the waves are all squished together. Okay, so high frequency is equal to high pitch. So like really high pitched sounds, like like a cat crying, or like some sounds that owls make, sometimes we can't even hear because the pitch is really high. So those are high frequency sounds which are here. If your wave is just like this, like really far apart, really slow, this is a low frequency, and this is a low pitch. So like it's a very deep, dull kind of sound. So some people that have like deeper voices, it's a lower frequency sound wave. And we can also detect sounds with microphones. So obviously, if you are speaking into a microphone, the sound is more projected and it's louder, isn't it? If you're speaking in front of an audience. And basically what happens is the sound causes a diaphragm to vibrate, and that produces an electrical signal. This is the diaphragm inside the microphone. So that's basically what it does. So normally you speak, but if you speak into a microphone, you just amplify the vibrations. Okay, so sound is all about vibration, and the more the vibrations, the louder the sound. Okay, so we can use sound waves for, sorry, does anyone have any questions so far, or are you guys all okay? Okay, yeah, please do ask if there are any questions. So what does amplify mean? Amplify means that you make it much bigger than it already is. Okay, so it's kind of like when you use a speaker, when you go to a concert, if somebody's singing, you can't hear them, but if they sing into the microphone, it amplifies it and it makes it much louder. Okay, so we can use sound waves for lots of different things, for detection and for exploration. So what can you guys see over here in this image? Excellent. So this is an ultrasound of a baby. Okay, so the if any of you guys have ever been with anyone who has been pregnant and they have an ultrasound, basically there is a probe that is put over the tummy, okay, and you put over the tummy and this image appears. So you might be thinking, how do we generate this image? Well, this is to do with ultrasound waves, okay, so this is a really, really useful property of ultrasound waves. Now, it has got the word sound in it, but it's also got ultra. Now, the reason is because ultrasound waves are sound waves which have a frequency higher than the limit of human hearing. So they are higher than what we can hear. They are at 20 kilohertz. Okay, so we can't actually hear anything that comes out. Can you see our limit is 20 kilohertz? So we can't hear the sounds from the ultrasound. So very high frequency ultrasound is used by doctors to explore inside our bodies. And the ultrasound is directed towards an organ in a narrow beam. Okay, so this is a very useful property. So if anyone has had an ultrasound, sometimes you can get it done of different parts of your body, like if you injure your knee or something like that, and you can't hear anything. Okay, it's very silent. When they put the ultrasound on you, it's not like you hear loud sounds because we can't hear it. So there are sounds, but we can't hear anything. And a really interesting question which says, could animals hear it if animals were to get an ultrasound? Yes, they probably could. If their frequency was higher than, if they could hear higher than 20 kilohertz, yes. So like, for example, dolphin could. So at each surface, some of the ultrasound is reflected and some is transmitted. So let's just have a look at that. So basically, this is your object. So let's just say this is like this is a mum who is having a baby. Okay, so you want to scan and look at the baby. So ultrasound is used for fetal scanning, that is to check the fetus. Now, the reflections are detected at different times and a computer builds up an image of the organ without the doctor having to look directly. So basically, I had to do these when I was working in maternity a few months ago. So you basically just put the probe there and then you just wiggle it around the tummy and it actually just appears on the computer and you can see it quite clearly. Like you can see the baby's heart beating and you can see like if it's kicking or it's moving its hands. And the reason this works is because basically the ultrasound sends out waves. Okay, these are sound waves. It hits the object, it hits the mum's stomach, and the waves get reflected back. Okay, they get hit back again. And these are reflected at a different frequency, and they get absorbed by the probe and they go into the computer. And then like the computer just generates the image. So this is very useful. And does anyone know any risks or anything? Do you guys think that this is dangerous to put an ultrasound scan on a baby? So yeah, a lot of you are saying that there could be radiation or the baby could be affected, but actually there is actually no radiation from this. So this is not like other types of scanning, which we'll talk about later when we talk about electromagnetic waves. It's not like CT scanning or X-rays which have radiation. Okay, this ultrasound does not release any radiation. It is just using the property of sound waves. So it's actually very safe and it does no harm. Okay, so putting this probe is a very safe technique. So it's very useful for us and this is why we use it all the time. Okay, so ultrasound is one example of using sound waves. Another one is ships use beams of ultrasound for a variety of purposes. So you can basically like look for fish, you can see like how deep is the ocean, and you can also look for submarines. So let's just have a look at that. So for example, so here we've got a ship and it is in the ocean. Now what this ship will do is a beam of ultrasound is transmitted by the ship. Okay, so the ultrasound, the rays are coming through like this. And what happens is as soon as you reach the seabed over here, because of the property of the sound waves, they get reflected back off. Okay, they hit the seabed and then they come right back through. Now, basically, what we can therefore work out is the longer the delay between the transmitted, i.e. the ones that go through, and the reflected, i.e. the ones that come back, the greater the depth of the sea. Okay, so if, for example, we take our ship, okay, and we put it over here. So let's say the ship was here. So obviously, if it has to hit the ray all the way down here, then by the time it comes back up, it's going to take some time, isn't it, compared to over here? So they can then work out, like, actually, oh, the ship is the depth of the ocean is much higher over here. It's 300 meters here, but actually at this point, it's only 150 meters. And this becomes very useful if they want to, for like looking for other, like looking for fish, or for doing any building or mining, or looking for anything in the ocean. Okay, I just want to do a quick question before we cover this stuff. So figure 1 shows a set of tuning forks. A tuning fork has a handle and 2 prongs. It is made from metal. When the prongs are struck on a hard object, the tuning fork makes a sound wave with a single frequency. The frequency depends on the length of the prongs. Use the correct answer from the box to complete each sentence. The frequency of a sound wave determine its what? So we did talk about this one. So the frequency of a sound wave will determine its pitch. Excellent. So if my wave is like this, it will be a very high-pitched, squeaky sound. If my wave is like this, it will probably be a dull, more deeper sound. Okay, this is pitch. The amplitude of a sound wave determines what? Excellent. So the amplitude determines the loudness, okay? And this is very intuitive to understand. If my wave is just like this, okay, yeah, there's a bit of sound coming out. If my waves start to become really deep and go up and down, okay, the amplitude, remember this is the normal, this distance is much bigger. This is what amplitude is. Okay, can you guys see that? So the amplitude here is much higher. Now, the frequency of both of these is the same. Can you guys see the distance from one peak to another is the same, pretty much. So the pitch of both of these will be the same, but this sound will be louder. And once you start squishing the waves together, that makes the pitch higher. So both of these are very different things, okay? And it's really important to become confident with understanding them. Does anyone have any questions? Because we did get a few mixed answers. Okay, so yeah, we've got pitch and loudness. Okay, each tuning fork has its frequency engraved on it. A student measured the length of prongs for each tuning fork. Some of her data is shown in the table. Describe the pattern shown in the table. Okay, what is the pattern that you guys can see? So I used to love these describe questions because I think these are easy marks. Okay, so when you have to describe something, you don't need to use your own head or any knowledge. You just look at the table and you just look at what is the table showing me. So I can see here as the frequency is going up, what is happening to my length of the prongs? The length of the prongs is going down, right? So the pattern is as the length of prongs decreases, okay, the frequency increases. Okay, so the shorter I keep my prongs, the more higher pitch you make the sound. So that's why these really short prongs, if you have a play around with these in music or in school, these little ones, the pitch is much higher, and when you bang these ones, the pitch is much lower. So you can just play around with them. Okay, so figure 2 shows a full-size drawing of a tuning fork. Measure and record the length of the prongs. So I'll just tell you that because obviously you can't do that on the screen. So this is about 8.3 centimeters. Okay, use the data in the table above to estimate the frequency of the tuning fork in figure 2. So this length of prong is 8.3 centimeters. So if we've got something that is 8.3 centimeters, what do we think the frequency will be roughly? So 8.3 is just sitting in between these two. Oh, sorry, it's sitting in between these two. Great, so any answer between 384 and 480 would get you a mark. So anything between 384 and 480. So I'd probably just say something around like 420 and just keep it right in the middle, because 8.3 is exactly in the middle of these two numbers. Yeah, it's 0.4 centimeters on either side. So I would just say around 420 hertz. And yeah, that is your answer. So 8.3 centimeters is between 7.8 and 8.7. So the frequency must be between 380 and 480. Okay, guys, it's just past 12 o'clock, so we will stop there. And if you guys come back at 1, and we will continue with where we've left off. So enjoy your break, and please leave any questions in the chat. I will see you guys soon. Hi everyone, welcome back. So I hope you all had a lovely lunch break. We are going to continue with where we left off. So just a little bit more on types of sound waves before we move on. Okay, so we talked about ultrasound and how useful it is, and how we can use it in not only in healthcare but also in when we look at the in the sea as well. One other type of wave, which is just links in with sound waves, is something known as a seismic wave. Has anyone heard of the term seismic wave, or what does it mean to you? Just throw any keywords at me. Okay, some good answers so far. So, when we talk about seismic waves, the main thing that I want you guys to remember is that seismic waves are the waves that are produced by earthquakes. Okay, so when we have an earthquake, which you may have heard of in the news in other countries, when there is an earthquake, what is the main thing that happens in terms of sound? So, are earthquakes quiet or are they very loud? Excellent. So, whenever we have an earthquake, there is a huge rumbling of sound, isn't there? It is so loud and it causes so much destruction. Okay, so seismic waves, they are produced by earthquakes, and these types of waves, they are very loud, they have a very high amplitude. And because they are have so much energy and so much vibration, this is why they cause an earthquake. Okay, and this is why they cause a lot of destruction. They can destroy people's homes, people's lives, even disrupt mountain structures, and etc. Okay, so seismic waves are a very, very powerful type of wave, and they have a lot of similar properties to sound waves. Okay, because they are basically very, very large sounds. Now, so when we hear about an earthquake, we usually just think about the destruction that an earthquake can cause, but earthquakes are actually tell us a lot of information about the Earth's structure. Okay, so basically, in terms of seismic waves, I've actually given it away, but there are two types of seismic waves. We've got P waves and we've got S waves. Now, the P waves, they are a type of seismic wave. They are longitudinal. Okay, and what did we say about longitudinal? Longitudinal waves have got rarefactions and compressions. Remember, they go back and forth. Okay, there are compressions here, and these are the rarefactions. P waves travel at different speeds through solid and through liquid rock. Okay, you might think, well, why do I care about that? But we will see how important this is later on. We've also got S waves, which are transverse seismic waves. Okay, so you can remember the S. Actually, that doesn't work. So S waves are transverse seismic waves. Now, transverse, as we said, is they go up and down. Okay, you remember that slinky, the wave is going up and down. Now, interestingly, S waves can only travel through solid rock and they do not go through the liquid. So, what does that mean through us? So, when we look at the Earth, okay, so as you know, this is your Earth. You're used to seeing it with blue bits, which denote the ocean, and then we have got green bits, which denote the land, right? That is usually what our Earth looks like. If we were to take a cross section of the Earth and look at the Earth at its core, this is actually what we would see. You would see this whole diagram over here. Okay, so if we were to chop up the Earth, you would see that it actually has got three major layers. Does anybody know what these layers are called? Fantastic. So we've got mantle, crust, core, really good so far. So basically, we have got the outer layer, okay, which is known as the mantle, okay, and this is solid. So basically, the outer layer is all of this bit here. Okay, this sort of light beigey color. Okay, this is known as a shadow zone. We'll leave that bit out, but this is all the outer layer over here. Okay, now this mantle is solid. Okay, so because it's solid, the P waves can go through. P waves go through liquid and solid, and so can the S waves. S waves only go through solid. We then have our next layer, which is the liquid outer core. Okay, so this bit here, let me just change my color. This is my liquid outer core. Okay, and this area, as it says, this is a liquid. So if it is a liquid, that means only the P waves can travel. We then go further inside, okay, and we have got our inner core over here. This inner core is also made of a solid. Now, if it's only made of a solid, that means that only P waves can travel through this bit, okay, because S only goes through solid only, but because it was unable to get through here, it cannot get through this. Okay, so what we can see is if we follow the diagram on here, so here in green we have got P waves only. So P waves can literally, they will go from, here is my earthquake, okay, so let's just imagine this is like one area of the earth. The earthquake hits, i.e. we have got seismic waves. That is what an earthquake is. It is just seismic waves, and it's made up of P and S. So P and S are coming out and they're both going through. Both of them can travel through this, okay, because this is a solid. You then get through the liquid outer core, and only the P waves will remain. The S waves cannot get through here. We've only got P waves here, and the P waves will go right through the center. Okay, so this diagram is showing us the path of seismic waves from an earthquake at the point at the top of the diagram. So we call this top bit, this is the same diagram as before, it's just a bit more wild. So the epicenter is, this is where, this epicenter basically means where the earthquake happens. Okay, so I think recently there may have been an earthquake in Vietnam or in some areas there, so you can imagine that this is a country where the earthquake is happening. Okay, now when P waves enter the outer core, they slow down and change direction. So your P waves are coming through and they're sort of just going all over the place. Now, because of the liquid outer core, no waves reach the shadow zone. Now, basically what happens is that there is this area of shadowing. Now, what happens is because some of the waves, they can't get through the liquid, like the S waves can't go through here, there is this area which we just call a shadow region, which is just kind of blocked off. Because if you imagine a wave is coming like this, but it can't get through here, so all of this bit just remains untouched. So if people are over here, the earthquake won't hit them there. And basically what this tells us is that by investigating seismic waves, scientists have learned a lot about the Earth's structure. So if we never had any earthquakes, okay, we would never know that there are three layers to the Earth. We wouldn't be able to work this out. It's only because of an earthquake hits and we have seismic waves that then allows us to think, oh, okay, well, some of the waves aren't going through, some are going through. What does that tell us about the Earth? Okay, it means that the Earth is divided up into 3 layers. The first one being the mantle, the second one being the outer core, and the third one being the inner core. Okay, I'm just telling you what you guys need to know because I know this sounds a little bit confusing. So all you need to know is that Earth is made up of 3 layers. Earthquakes comprise of seismic waves, which are P and S. Okay, so through the mantle, because it's a solid, P and S can go through. The outer core is a liquid, so only P can go through. The inner core is a solid, so you would think that S waves can go through because S goes through solid, but because we have just gone through a liquid region, all the S waves are already just trapped in this area. They can't come through here, so they don't get through here. So only P waves go through the inner core. And through this, we worked out that there are different layers to the Earth and what is the Earth's structure. Okay, does anyone have any questions on this? Okay, so we're just going to do a quick quiz on sound and seismic waves, and we will then come back to talking about electromagnetic waves. Okay, let's see if we can get somebody else in the lead this time. All right, let's get started. So sound waves are all, okay, hopefully, I think we've done this to death, so hopefully everyone will get this one right. Okay, so sound waves are all longitudinal. So transverse waves are things like light and things like water. So sound waves can make your eardrum vibrate, make you want to watch TV. Fantastic. So sound waves are all about vibrations, okay? And you can imagine that your eardrum is just like a musical instrument. It's like a drum. Excellent. So we cannot see sound waves, okay? Have you ever seen a sound wave? I think the answer is no. So sound waves start with, excellent, they start with vibrations. If a sound wave is reflected back off a surface, okay, it's called an echo, and that usually tends to be a hollow or a substance that's got a very high ceiling, then you tend to get an echo. So sound waves that are louder have what? Excellent. So sound waves that are louder have a greater amplitude. High frequency sound waves are a higher pitch or a lower pitch? Excellent. So the higher the frequency, remember, the closer together those waves are, the higher the pitch. Excellent. So sound waves can travel through all different types of mediums. Okay, so even through a solid, even if you shout through a door to somebody in a different room, they might hear you. Even if you're underwater and you try and speak to somebody, the sound wave will travel. It will be muffled, but will travel. And obviously it can go through gases. Sound travels through air. So seismic waves that travel through the solid earth, is that P and S, P or just S? Excellent. So basically, P waves travel through solid and liquid. S waves only travel through solid. So the ones that travel through solid will be both P and S. So earthquakes produce two kinds of seismic waves. Is that true or false? Excellent, that is true. We have our P waves, which are longitudinal, and our S waves, which are transverse. Excellent, they produce earthquakes. So this would be our epicenter, the site of the earthquake, and these are the P and S waves radiating outwards. Fabulous. A lot of you got nearly 4 marks. That is great. Okay, so let us move on now to the next section that we're doing today. This is probably my favorite part of waves and the most interesting, I feel, which we have saved till the end. So we have talked about light waves. Okay, we talked about reflections and the mirrors. We talked about sound waves and amplitude and frequency. And we also talked about seismic waves. We're now going to talk about electromagnetic waves. Okay, so there are a few key points which I want you guys to remember. Electromagnetic waves, these are transverse waves, okay? Sound was longitudinal. EM waves are actually transverse, okay? And you can see the transverse waves over here. Now, there's not just one electromagnetic wave, there are several different types of electromagnetic waves that exist on a spectrum. Okay, so there is a range of them, and they're all very unique in their own properties. They all have different effects, and they actually have some very, very incredible uses. Can anyone give me any examples that you know already of electromagnetic waves? Fantastic. Electromagnetic waves, there are several. We've got infrared, we've got microwaves, gamma rays, X-rays, and UV rays as well, and a few more. So we'll be talking about all of these. So all of these are types of electromagnetic waves that exist on a spectrum, but they are all transverse. Okay, you never want to think that these are longitudinal, because that is the main property that they all have in common. Okay, now what about the wavelength of these electromagnetic waves? So it sort of varies from really, really short wavelength. Okay, if it's 10 to the minus 12, that's like 0.00010. So it's a very, very short wavelength to over 1 kilometer. Okay, so there is a huge amount of variation in our electromagnetic waves. And although electromagnetic waves have a wide range of frequencies and wavelengths, they all have important properties in common. Okay, so we've got several types of electromagnetic waves. There are 7 main ones, but all of them have these things in common. So this is what I want you guys to know for all electromagnetic waves. So as I've said again and again, they are transverse. Okay, all electromagnetic waves are doing is they're transferring energy from one place to another. Okay, there is never a movement of material. Okay, you are never carrying the wave from one part of the ocean to another. Okay, you are simply transferring energy back and forth. All of these, just like all waves, they obey our wave equation. Yeah, wave speed is equal to your frequency in hertz multiplied by your wavelength, okay, which is in meters. So we did this morning. Hopefully we haven't forgotten about it. So they all obey this equation. So you could get questions on the equation in this. Okay, they travel through a vacuum. Okay, what do we mean by the word vacuum? So when there is no air, a place where there are no particles, a place with no oxygen. Excellent. So all of the ways that we've talked about, okay, like sound, like light, etc., they can all travel through air, they can travel through a liquid and through a solid. But what about in spaces where you don't have any air, okay, or there's no water, there's no wood, there's no metal or anything. So we call that a vacuum. Okay, so a vacuum is basically when there is no air. So for example, in space is the main example. So all of these electromagnetic waves can travel through a vacuum. And the speed at which they travel through this space, this vacuum, is at 3 times by 10 to the 8 meters per second. Now, if you guys are doing triple science, you do need to know this number. They can't sometimes ask you. If you're doing double science, then they don't usually ask you, but it's just good to remember 3 times by 10 to the 8. Okay, so these are five main things that you guys should remember about all electromagnetic waves. Okay, they all have this in common. We're going to talk about the range of EM waves that exists now. So electromagnetic waves form a continuous spectrum. Okay, so spectrum just means a range, like the colors of the rainbow. It's just a different spectrum of wavelengths. Okay, now basically the only thing that makes one type of EM wave differ from another is basically the wavelength. So if the wavelength is longer, it will have different properties. If it's a short wavelength, it will have different properties. So this is the spectrum over here, and it's one to become quite confident with. So starting with the longest wavelength, okay, so longest wavelength is over here. Can you see it's long? The groups of electromagnetic waves are, we've got radio waves, microwaves, infrared, visible light sits in the middle, and then we've got UV, X-rays, and gamma rays. Okay, so these are basically the 7 types of electromagnetic waves that exist, and they're all the same basically. They're all the same as each other. The only difference is in their wavelength. Okay, so what you can see here is that this is 10 to the minus 12, and this is 10 to the power of 3, i.e. it's 10,000. Yeah, this is like 0.000, like 12 zeros over here. So you can see the huge difference in their wavelength. Now, sitting in the middle, almost in the middle, is visible light. So you obviously they're saying it's visible because you can see the sun, can't you? So this is visible. Everything else, you cannot see it, okay? Like you cannot see a radio waves, you can just hear the radio, and you cannot see any gamma rays or any X-rays either. So our eyes only detect visible light, okay? So the only thing that we can see with our eyes, okay, is visible light. So they detect a limited range of electromagnetic waves. So all of these are very useful, but we cannot see them. Okay, we will talk about them in detail, but just very briefly, does anyone know which of these are sort of the most dangerous? Do you think it would be gamma rays, or do you think it would be radio waves? Excellent. So gamma rays are actually the most toxic actually, and they can make you very sick, and you can die from exposure to gamma rays. X-rays we use very frequently, but in medicine we use them a lot, but they do have their own drawbacks. So we don't just give everyone an X-ray for no reason. There has to be a strong indication, because X-rays, if you have them again and again, they can be very damaging. Okay, we can contrast that to, if we come over to the right hand side, things like radio waves. These are very, very low risk. You can keep the radio on all the time. It probably won't do anything to you. But we move across to microwaves, which there is a lot of debate about, that they are quite dangerous if you heat your food in them consistently, but this is debatable. And then infrared, which is heat. Okay, so that is just an overview of our electromagnetic rays. Now, A few properties of our electromagnetic waves. Now, we touched on this in one of the exam questions earlier, but this is where we go through it in detail. Now, a property of electromagnetic waves is refraction. So, when waves travel from one medium to another, they usually change direction. We saw that earlier. So we had the waves traveling through air. And then do you remember when it went in that glass box in that exam question, they went all the way together and then they came out and they went to the same, okay? Because when waves go from one medium, they usually change direction. And this effect is called refraction. So this movement from one direction to another, once you change the medium, is called refraction. And different wavelengths refract at different angles. So depending on which electromagnetic wave you have, the degree of refraction will vary. So for example, what you can see here in this spoon, okay, so basically what has happened is you put the spoon in here and it's traveling through glass, so it's over here. You then change the medium, so this is glass and it's basically traveling through air. You then put in some water in the cup, and can you see how, obviously in real life your spoon will still sit here, won't it? But because of the change in medium and the change in the angles, the spoon actually looks like it's over here, which is very interesting, and this is known as refraction. The spoon is not actually here, it's actually here, but it's just the way it appears to the eye because the angle at which the wave has moved, and it's causing it to bend over, okay, because it has changed direction. And this is refraction in action, okay? This is what it actually looks like. So another example, so we see rainbows because the different colors of light, which have different wavelengths, are refracted through different angles. So that's why all of the colors in the rainbow appear different, because actually they're all the same. They're essentially just waves of light, but it's because like red will have a different wavelength compared to yellow. And that's why it all looks different to our eye, but it's actually just the same thing. So just a little bit more on that. So different wavelengths of visible light behave differently when they are incident, i.e. when they occur on various surfaces. So this is why in terms of colors, a red shirt appears red because red light is reflected, and all other colors of light are absorbed. Okay, so basically if we imagine that this is my t-shirt over here, okay, now when light hits this t-shirt, okay, you can just imagine that this is my sun over here. Now when light hits the t-shirt, okay, light contains all wavelengths of the spectrum, okay, so it contains everything, but what happens is that all of the other colors will be absorbed, so like blue, green, yellow, all of the other colors that are here will be absorbed, and only red will be given off, and that's why the shirt looks red. Okay, so a polished metal surface reflects most electromagnetic waves, and wavelengths from radio waves to ultraviolet are reflected by metal. So most of the ones on the spectrum are reflected. So things like gamma rays and the other one, X-rays, they don't tend to be reflected by normal objects because they're very high frequency and they're quite toxic and dangerous. So we're just talking about the ones that are lower frequency waves and that are safer. Okay, and just a little bit of a bit more on this. So X-rays and gamma rays, they are able to pass through the thin metal because these are very, very powerful rays. So when a potato is cooked in a microwave oven, the potato is absorbing all of the microwaves, okay? And that is why your potato gets heated up. So the wavelength of the microwaves is carefully chosen so that the water molecules in the food absorb them. So this is why if you next time you look on your microwave, you'll see you have lots of different settings, like one for defrosting, one for doing like a quick heat, one for heating up more intensely. And that is basically because different wavelengths of the microwave are being released depending on how hot you want to make something. So this you can imagine here This would just be like the potato, and this is the microwave. Okay, sometimes with transmission, if you imagine this is a piece of metal, and the X-ray and the gamma ray will go straight through it. Okay, this is how X-rays work. So when next time, if you get a chance to go to the airport, probably not soon, but when you go through the airport and you go through security, you walk through those metal gates, right? Because they are releasing an X-ray as you walk through, because it will go straight through your body and it can pass through. Other types of electromagnetic waves will be reflected. So obviously things like light will be reflected off a surface, and that's how we can see things. Okay, so I just want to talk a little bit about refraction, because this came up earlier and this is a important concept in waves. Okay, so we said that things can be reflected, they can be absorbed, and they can be transmitted. Okay, the other thing that can happen to a wave is that it can be refracted. So the diagram shows how light is refracted as it passes through a rectangular block of glass. Now, basically what's happening here is, again, this is my ray box. This is what we talked about in the morning, and this is your glass block. So normally you think that this is your angle of incidence, and then this is your angle of reflection, right? Now, if something is transmitted, it would just go through like this. It would just follow this path, and this is known as transmission. What you can see here is that this wave, not only has it gone through, but it has changed angle and it has changed its direction. When a ray changes its angle and it changes its direction, this is what we call refraction. Okay, and refraction occurs when you move from one medium to another. So you can see that instead of just following this path and going through, it has decided to change its angle and just go somewhere completely else. And this is what we call refraction. Again, as it comes out of the glass block, it has changed its angle here. So if we were to start from here, you can see that your light ray was actually here, but as you put it through the glass box, it actually came out over here when you would have expected it to just come through here. So can you see the amount of difference between this? And this is the power of refraction. So the angle between the incident ray and the normal is called the angle of incidence over here. And the angle between the refracted ray and the normal is my angle of refraction. And this is what came up in that past paper question earlier this morning. Okay, why does this happen? Like, why is it that the light can't just behave and go through like this? Does anyone have any idea? What causes it to bend through like that? So the different medium, because of the density is different in the air, causing the ray to change. Excellent. So basically the reason is that why does that happen? Well, the light is refracted when it enters and leaves the glass, because the speed of light in the glass is different to the speed of light in air. Okay, so the light can travel, the speed at which it travels through the air is different through the speed at which it travels here, and that's what messes it up. So light changes direction towards the normal when it enters the glass, because light travels more slowly in glass than it does in air. So if you look at it over here, it's traveling more slowly here and it's traveling more quickly here. So that's why it bends towards the normal. Now, as you come out of the glass, light changes direction away from the normal when it leaves the glass and enters the air, because light travels faster in air than in glass. Okay, so what will then happen is that here it is more quickly, and it's more slower here. So it then bends away from the normal. Okay, this is a bit tricky, so I'll explain that one more time. So light travels faster in air than in glass. Okay, air is greater than glass. So over here, it's going through the air and it's happy, it's racing through. It then hits a piece of glass and it thinks, oh no, I'm going through glass now, it's much slower. So because it's slower, it tends to come towards the normal, the angle tends to reduce, okay, it's only 35, so it slows its way down, trying to get through the glass. Now we're coming out of the glass and we're going back into the air, so it gains the momentum and it speeds up. Now because it can travel much more quickly, the angle increases. Can you see now it's 60 degrees, it was 35 here, and it was 60 because it's traveling much more quickly, so that angle goes up. Okay, so this is air, this is glass, and this is air. So going from air to glass, it slows down, so it goes towards the normal. Going from glass back out into air, it speeds up and it goes away from the normal, so the angle increases. Okay, does anyone have any questions on this? Because refraction is a bit of a tricky concept. Okay, but you guys are doing well, so I think that is okay. So yeah, so all types of waves show refraction, in particular the electromagnetic waves and the seismic waves. Okay, it's all to do with refraction. And water waves can also be refracted. So what you can see over here is that if you are swimming in a deep pool versus in like the baby area where the water is shallower, what happens is that the water waves become refracted. So when the water is deeper, the wave movements tend to be much faster, and in shallow movements, the waves tend to slow down. So in this case, the waves will slow down over here and they become shorter and they will change their direction. So as soon as it hits this change in medium, can you see that the waves will change their direction and they change their angle? Okay, the change in direction and change in the angle, these are the two things that happen in refraction. If not, it's just called transmission. If it just goes straight through and it went continuing on like this, we call it transmission. Okay, so going back to our actual electromagnetic waves, so we know their properties, we know that they are subject to refraction. So we're going to talk a little bit about radio waves and microwaves. So radio waves, as I'm sure you'll know, these are very useful when you listen to the radio, and microwaves are useful in heating up your food. So this diagram shows how radio waves and microwaves are transmitted and they are received. Basically, what happens is how do we actually generate these waves? It's a very complex mechanism, but a high frequency alternating current is supplied to the transmitting aerial. That's over here. So you give a high current, it has to be an electrical signal. Okay, so if you imagine, if you want your microwave to work, you need to plug it in, don't you? You need to plug it into the mains. And what this does is this makes the electrons oscillate. Remember, oscillation is that movement going up and down the aerial. Okay, now an electromagnetic wave is emitted, and this wave transfers energy in oscillating electric and magnetic fields. And this is a transverse wave, okay, because the oscillations are at right angles to the direction of energy transfer. So all of these, as we've said, these are all transverse waves. Okay, so this is our spectrum over here. And basically what happens is when the electromagnetic wave reaches that receiving aerial, the electric and magnetic fields causes the electrons to oscillate up and down. It just generates what we keep seeing in transverse waves. It goes up and down like so. Okay, and this induces a current in an electrical circuit. Okay, so you need a current. Obviously, you need electricity for your microwave to work, or even to plug in your radio. You need a battery power, so it induces a current. And the alternating current has the same frequency as the radio wave itself. So you may remember in a previous topic, we talked about alternating current and direct current and all of that. But it's very interesting that the frequency of this current is the same as that of the radio wave. And that's how you know like what radio station to listen to when you click on a different button. Okay, so radio waves also carry the information that we hear and see on radios and on televisions. These are both the same type of radio wave, just at a different frequency. Okay, so electromagnetic waves ranging in wavelength from infrared to X-rays, so we're talking about these ones, from infrared to X-ray, they can be generated or absorbed by changes in atoms. So all of these rays, they have the process that we just talked about that current. But with the gamma rays are a bit special. The way that they work is slightly different. And basically what happens is a gamma ray is generated when there are changes to the nucleus of an atom. So you may have heard of gamma radiation of being as radioactive. Okay, does anyone know what we mean by radioactive? So essentially, radioactive material is material that basically it is emitting neutrons. So what can happen is that some of these, some substances in the atmosphere, they are radioactive, which means that they've got extra neutrons which need to be removed from them. And each time these neutrons are removed from the nucleus, energy is released and the particles become radioactive. And this radioactivity can actually be very, very dangerous and very toxic. So we can use gamma rays to destroy cells in the body, like for example cancer cells, but it can actually make you very sick because it can destroy most of the cells in our body, because our cells are also made up of electrons, protons and neutrons. So the gamma ray will trigger the neutrons to be released from our own cells as well. So what you need to remember is that gamma rays are generated when there are changes to the nucleus. Basically, it's a removal of a neutron. And so when a gamma ray is emitted, the nuclear energy store of the atom decreases. So each time the neutron is removed, energy is released, and the energy store of this nuclei reduces. However, gamma rays are given out, and those gamma rays can make us sick. Okay, guys, it's just turned 1:45, so we're just going to go for a quick 15-minute break, and we will then continue with the just continue where we left off. So I'll see you guys back at 2. Hi guys, welcome back. So we are on our last hour, so well done if you are still here with me. We've got an hour left where we're going to be wrapping up what we have talked about electromagnetic waves and doing a few other bits. So we've talked about our 7 waves on the electromagnetic spectrum. Yes, they have their uses, which we have talked about, but there are also some hazards of electromagnetic waves. So can anyone tell me any hazards that they know of? So I'm getting some really good answers. So some of you said can cause cancer, ionization from gamma rays. Now, too much exposure to some types of electromagnetic waves can in fact be very dangerous. Okay, if you're going to get an x-ray of your chest or of your leg every day, it's going to be dangerous. If you get a one-off x-ray, it's fine, but if you keep getting it done, it can be dangerous. Now, the way we work out which rays are dangerous and which are not is by looking at their frequency, okay, because that is the only difference in our types of electromagnetic waves. So the higher the frequency of the radiation, the more the damage it is likely to do to the body, okay? So this is why when we look at our spectrum over here, okay, the ones that have the higher frequency, this is written the other way around, but the ones that are higher frequency, i.e. the gamma rays, are much more dangerous than the radio waves, okay? You can keep your radio playing all day long and it's fine, but any even slight exposure to a gamma ray can be very dangerous. Okay, and that is to do with their frequency. So the UV light, okay, UV light comes from the sun. This is why you're advised not to sit in the sun all day without any sun cream or any protection. X-rays and gamma rays, these ones are the worst and they have got the highest frequencies, okay? Their waves are closer together. So UV rays, X-rays and gamma rays, why are they all dangerous? Because they can cause mutations to our own cells. So we've got a bit of biology coming here. So tell me, what is a mutation? So mutation is a change, that is right. And what is it a change in? A mutation is a change in the DNA or in the genetic makeup of a cell. Okay, so just very quickly, this is my cell. This here is my nucleus. Yep, this is my cell membrane. Inside that nucleus, I have got DNA. DNA is made up of these bases. Okay, if we change one of these bases, you might think, what's the big deal? But actually, it can affect the whole functioning of the cell. So if we were to just swap something around or get rid of one of them, it would really mess things up. So all of these rays are very powerful. They penetrate straight through the body. Okay, so you can't see them, but they can go right through your skin and into your heart, into your lungs. They go everywhere, and they cause a change in the DNA. Now, once there is a change in the DNA, you're basically in a mess because all of your cells will replicate with that messed up DNA, and it can make you very sick. Okay, and that uncontrolled cell growth is what we call cancer. Okay, normally a cell will divide in a very controlled way like this. Okay, if you have got cancer, the cells, they will grow uncontrollably. Okay, and they will all be cells that are messed up, and that is purely because of a mutation. Okay, so I want you guys to remember ultraviolet, X-rays and gamma rays. These are very hazardous EM waves, okay, in relative to the others. So what can we do? So we are most likely to be exposed to the UV rays when we are in the sun, obviously. Okay, so people who live in more warmer climates or who spend their days on the beach are more exposed to UV rays. Now, ultraviolet rays, because they hit our skin, the main problem that they can cause is skin cancer, and they can also cause your skin to age prematurely. So prematurely means earlier than it should be. So your skin can become very droopy and quite tired looking, and you have a much higher risk of skin cancer. Does anyone know, out of interest, what types of skin types are more prone to cancer? So do you think it is people with lighter skin or people with darker skin? Interesting. I'm getting some mixed answers. So actually, people who have got lighter skin, so Caucasian people, or people whose skin is, as you would say, white, are much more prone to skin cancer than people with darker skin, who may be like Afro-Caribbean or South Asian. And this is purely to do with what we have learned about light waves and absorption. Because remember, we said that the lighter surface will absorb the rays, and this is why people with lighter skin will have got a higher risk of skin cancer. And excellent. So darker skin has got more melanin as well, which is protective. So things that we can do to protect our scales. So it is lighter skin that is prone to it, but obviously we all need to be careful. So we take precautions against UV radiation by basically wearing sun cream is the main thing that we can do. You can also wear sunglasses to protect your eyes, and also to limit the amount of time that you spend in the sun. So usually, you're recommended after 25 to 30 minutes of directly being in the sun to go in the shade. And a lot of people, even if they don't get skin cancer, they can actually get they can get sunburn or skin burn, where the skin becomes very red easily because it is quite sensitive. So yeah, just taking care. So staying in the shade between peak hours, covering up, wearing sunglasses, wearing a hat, and using sun protection. Okay, so that is UV rays. So remember, there are three waves which are the dangerous ones. UV we've talked about, X-ray and gamma rays. So these ones we are at highest risk from, because obviously the sun is everywhere, and we are much more exposed to it. Now, we're less likely to be exposed, to accidental X-rays or gamma rays. If you are going for an X-ray, you will know that. You're not just going to have a random X-ray thrown at you. So X-rays and gamma rays are used in medical procedures where suitable precautions are taken to reduce the risk to our health. Does anyone know what types of precautions we can take if we are using X-rays? Wow, I'm really impressed. So a couple of you said surrounding the room with lead or using lead covers. Excellent. So usually what happens is, because when somebody is, if this is a person who is sick and this is the X-ray machine, okay, so the X-ray will basically just flash, will go through the image, will go through the person, the images appear on the computer. But obviously for somebody to work this machine, there needs to be a person there, right, to switch the machine on and to run the whole process. So this poor person who works inside the department is all like at very high risk, because they are always by the X-ray machine. So to combat this, okay, to make it fair, we have lead barriers. So the walls of the room, and there are barriers which are made of lead. Now, why do we make it of lead? Well, it's because the X-rays cannot penetrate through the lead. They cannot go through. Lead is a very highly dense substance, and it's a very good absorber of the X-rays. So none of the rays will come through, and this person will be fine. So yeah, we've got lead barriers, and there's also specific clothing and eye protection that people wear as well when they're in this area, which is made of a fine coating of lead as well for added protection. Great. So this table just sort of summarizes what the dangers are. So as you can see, radio waves are fine. Microwaves, because we just use them in the microwave, there can be some heat damage, but this is not really proven or anything. So microwaves are okay. Infrared, okay, can cause skin burns because of the heat. Visible light, if you look directly into the sun, you can damage your eyes, so you don't do that. And then UV, X-ray, and gamma, these are the ones that can cause problems. So ultraviolet can cause skin cancer, and the X-rays and the gamma rays, they can cause any type of cancer in the body. So it's not just for the skin, because they cause mutations everywhere, so they can destroy cells. Okay, so just talking a little bit about radiation dose. So as we've said, X-rays and gamma rays, these are ionizing radiations, okay? That means that they are using ions to release the energy. Now, the damage that these types of radiations do to the human tissue will obviously depend on the dose received. Okay, so the more you are exposed, or the higher amount of the ray that you receive, the more damage will be done naturally. There is a unit that we use to measure the radiation dose. Does anyone know what this unit is called? Well done. So this, the effective irradiation dose is measured in something called sieverts, which is SV. So sieverts is just the unit for measuring radiation dose. And what we know is that, so on average, we receive a radiation dose of about 2 million sieverts per year from background radiation. So background radiation is just what naturally exists in our day-to-day life, because you don't know where you are going and we cannot see any of this radiation, but we think that in a lifetime you might be exposed to this much. And this dose is thought to be safe, but larger doses can cause harm. So what you can see here is that if you were to go for a CT scan, okay, which is like a powerful scan to look into some parts of your body, it is 7 million sieverts. Okay, so this is a lot of radiation, because most people are exposed to 2 in their whole life. If you go for one scan, you'll already be exposed to 7 million, and typically people have several of these if they are unwell, so it really increases their radiation dose. Even, for example, a chest x-ray is 0.1 MSV, so it's very, very low, 0.1, but the more x-rays you have, obviously you're basically building it up, and it just builds up in the body. And the main concern is people who sort of work in like nuclear plants and in these building sites where there is a lot of ionizing radiation. So this is like a nuclear plant. I don't know if you guys know anybody that works there, but you can see that the 5-year dose limit is 100 million sieverts. So it's quite a lot of radiation that they're exposed to. And sometimes if people get very sick from working here, they actually they can try and get some money back and things like that, because they've been exposed to this at work. Okay, so we've talked about the dangers. Let's talk a little bit about uses and application of our waves. Okay, so there are many, many uses of these electromagnetic waves, although they have their downsides. So firstly, with our radio waves, as we already know, we can use radio waves to listen to the radio and also for TV signals as well. So radio waves are used to send radio and television signals from transmitters to our homes. So have you ever thought about as soon as you put the radio on, the music plays, but basically what is happening is you have these satellites in like the countryside or in remote areas. They transmit microwaves, okay, to a carrier satellite, and this then carries a signal into our home. So you never actually see these, because you cannot see a microwave with the naked human eye, but they are there. And they are called terrestrial as they go across the ground, so they can go through the ground. Terrestrial just meaning terrain, like Earth. And radio waves can be transmitted over long distances by reflecting them off the ionosphere, which is a layer in the Earth's atmosphere. So this top layer on the top has got something known as as an ionosphere, and the signals can literally just go through here and directly through people's homes. Okay, and microwaves. So we've talked about radio waves. Microwaves are used for satellite communications as well because they pass easily through the Earth's atmosphere. So microwaves are not just used, for cooking purposes, as you can see over here, but they're also used sometimes in mobile phone networks as well, and also in satellite television. Okay, and you can see this is a microwave here. So the frequency of it is not that high. Okay, it sits in the middle. It's about 10 to 2. If we go further along the spectrum, the waves will be much closer together. And this is basically just showing a microwave going along. And yeah, so as we said, microwaves are used in the home to cook food in microwave ovens. And the way that it works is that as soon as you put your microwave on, some wavelengths of microwaves are absorbed by the water molecules. So in, like, for example, if you put in like some pasta, there is always some water there is always some liquid form, and that is absorbed by your food, and it therefore causes heating of it. Okay, so we also use infrared waves, which are just like heat waves, to provide heating from electrical heaters. And so microwaves use microwaves, but ovens, they use infrared radiation. So next time you put your oven on, just remember that you're using heat radiation. You may have heard of other uses of infrared as well, in particular with cameras. If you want to take a photograph at nighttime, obviously there's no light, so nothing can be seen, but we can use infrared cameras which just use the properties of heat. So you may have seen like images like this, which are very odd colors because they're not the real colors. It's just the heat energy that is absorbed by this cow and the grass. You also use it for CCTV cameras as well. We use infrared, and also in remote controls too. And just a few more. So we've talked about infrared, we talked about microwave, and light waves as well. So light waves are used obviously for us to see things. If we didn't have light waves, we would all be in the dark. And light is also used in fiber optic communication systems, things like telephone links, and wiring, fiber optics, and yeah, things like that. Okay, so okay, we'll come back to these. I just want to do a few questions because I'm worried that you guys are getting a little bit bored. Okay, so the figure below shows an incomplete electromagnetic spectrum. What name is given to the group of waves at the position labeled A in the figure above? So tell me, guys, what do you think should be labeled over here? This is the spectrum, okay, so it's in order. So think back to your spectrum. Excellent. So just sitting next to microwaves are radio waves over here. Okay, fantastic. And just for completion, if these are microwaves, what comes just after microwaves? So what would B be? Okay, some of you are saying X-ray, so just be careful. Think about where you are on the spectrum and think about your frequency. If this is gamma, these are the high frequency toxic waves. This is radio, these are those low frequency safe ones. Fantastic. So this is infrared. Remember those infrared beams, this is heat. What sits right in the middle, just between the UV, between the sunlight and the heat? What sits in the middle? Excellent. Visible light sits right in the middle. Okay, and if this is gamma, what must this one be? The one that's just slightly less worse than gamma rays. Excellent, X-ray. So that is your spectrum. So do learn this because as we can see, this does come up. So the correct answer here, labeled A, is radio waves, and we know it cannot be any of these because we filled them in. Okay, electromagnetic waves have many practical uses. Draw one line from each type of electromagnetic wave to its use. Okay, gamma rays. What is the use of gamma ray? So this is actually a really tricky question because we have already covered the main the main uses, but actually none of what we've talked about has come up. So this is why it's good to do the questions. So gamma rays, what we know is that gamma rays are used in healthcare, but they can be very toxic. Because they cause mutation, so we only use a small amount. So just by process of elimination, we know they're not used in fiber optic. We know they're not used in satellite. We cannot use them for security markings because they are very toxic, aren't they? We're not going to be using them for things like this. The only thing that we would use it for is to sterilize surgical instruments. Because what do gamma rays do? Gamma rays are very powerful and they can destroy cells. So if a surgeon has done an operation, okay, and then they want to use that equipment again, they need to make sure that it's clean, right? So that no infection goes to the next person. So gamma rays are very, very strong and they will really clean that equipment and kill any like remaining blood or like whatever is on the cell, on the instrument. Okay, so gamma rays sterilize surgical instruments. Well done. Okay, microwaves. What do we know about microwaves? So we know it can't be the last one. Which one do you guys think it will be? Fiber optics, communicating with a satellite, or to see security markings? Fantastic. So microwaves, as we've said, microwaves can be used to heat your food up in a microwave, but not just for that. They're also used in telephones as well. And the way that they work is through communication via satellite. So we did see that diagram earlier. So microwaves are for communicating with a satellite. Okay. And ultraviolet rays, finally, what can you use UV light for? Do you think it's for fiber optic communications or for security markings? Yep, so we will come on to I'll show you guys a few more on UV light. So UV light is actually very bright penetrating light and it is visible. So UV light actually tends to be what we call fluorescent. Okay, so you may have had like a fluorescent jacket if you go bike riding or anything bright like that, and it emits UV light, which is actually really helpful, like to solve crimes if you're like at a forensic site, or to look at something like on an image if you want something to stand out. So the UV lights are actually used to see security markings. Okay, so if you've got a security tag and there's like a mark on it, you can put the UV light to see if it lights up, and you will know if it belongs there. Okay, so tricky question. Well done, guys. So complete the sentence. Use an answer from the box. X-rays can be dangerous to people because X-rays are what type of radiation? Okay, do we think it is A, B, or C? Excellent. So X-rays are ionizing radiation, okay? They cause the removal of an ion when they hit the cell or the source. So X-rays and gamma rays, these are ionizing forms of radiation. Okay. Figure 1 shows an X-ray of an arm with a broken bone. Complete the following sentence. X-rays are part of the what spectrum? Okay, hopefully everyone can get this. Excellent. So X-rays are part of the electromagnetic, or the EM. So yeah, I do say EM because it's quicker, but don't write down EM in your exams because you won't get the mark. That's just a short form. Oh, actually, they said accept EM, but I think we should write electromagnetic. Okay, so figure 2 shows how the intensity of the X-rays changes as they pass through soft tissue and reach a detector. Use figure 2 to determine the intensity of X-rays reaching the detector for a 3 centimeter thickness of soft tissue. Okay, what do you guys think? This is question 10 of your question packs if you want to have a go on the graph. Great. So basically what you have to do is just make sure that you read the graph really carefully, otherwise you'll basically just get the units the wrong way around. So on the x-axis, we've got thickness of soft tissue, and on the y-axis, we've got intensity of X-rays. So they're asking us to calculate this, so don't put 3 here and then match it up, okay? You'll get it wrong. It's the other way around. So it's 3 centimeters, so you need to start here, okay? And then you just match it up. So you make sure you use your ruler in the exam to do this. And basically you will get, these are divided, there are 10 units divided up into 5, so each one is worth 0.2, so it would be 2.2 arbitrary units. Basically what this is trying to show us is that the thickness of soft tissue, so like if somebody is a skinny person, they don't have much tissue, so the x-ray will go through them straight away. If somebody is like a bit much more larger person, okay, this is like a bigger person, it will take longer. It's harder for the x-rays to penetrate through them because they've got more soft tissue. Okay, I've just given this one away. So describe how the thickness of soft tissue affects the intensity of the X-rays. So this is a describe question and it's 2 marks. So how does the thickness of soft tissue affect the intensity of the X-ray? So I'll just go back to the question again. Describe how the thickness of soft tissue affects the intensity of the X-rays. Fantastic. So basically, the thicker the soft tissue, the lower the intensity. Okay, so with this describe question, essentially all I would suggest you do is look at what's happening on the x-axis, and then look at what's happening on the intensity, and then look what's happening on the y-axis. So as you increase the thickness of the soft tissue, the intensity of the x-ray reduces. Okay, and to get the 2 marks, you need to have both of the points linking together in a statement like this. Okay, the data in figure 2 are shown as a line graph and not as a bar chart. Choose the reason why. Okay, so just to remind you guys, this was the chart here. This was my tissue. This was my X-ray. Why did they use a line graph and not a bar chart? Do you think it is A, B, or C? Do you guys know what we mean by categoric and continuous? So it's good to do these exam questions because they always like to put in experiments and talk about data. So basically, there's two things here. There's a line graph and there's a bar chart. This is what we call a line graph, and this is a bar chart. Okay. Now there's different uses for each of these. So the question is saying, why couldn't we put tissue here and X-ray here and do it as a bar chart? Now, would that make sense? The answer is no, it wouldn't, right? It doesn't make sense. If this is 1 centimeter, this is not the number of people that have that amount of X-ray, right? It doesn't make sense. So we know we can't do a bar chart. The reason is why. Now, the key terms used here are continuous, categoric, and variables. Okay, what do each of these things mean? Let's start off with variable. Variable is something that you change. So either you can change the tissue thickness will change and the penetration of the X-ray. These are variables, okay? They're things that change in an experiment. If you want to see how fast you can run on a hot day versus a cold day, the temperature is a variable, okay? Your distance of running is a variable. All of these things are things which we change. Now, either things can be categoric, which basically means they are categories. Now, categories are things like color, okay? Either it's blue, it's black, or it's white. Or it can be something like shoe size, okay? Either you're a size 5, you're a size 6, or you're a size 4. Or it can be your gender. Either you are a male or you're a female, okay? There are not several ranges of things, there are fixed options. That is a category. Other times, a variable can be continuous. Continuous is basically it continues, and these tend to be numbers. So like your height, it can be 150, 151, 151.1, 151.2. It can be your weight. Okay, so things like 56, 57, 58, 59. So these continuous, they tend to be like numbers which follow each other continuously. So similarly, now that I've given you these definitions, do you think that the length, the amount of the tissue, is it continuous, or is it a or is it categoric? So remember, the tissue, as we saw in the graph, it's like 1 centimeters, 1.5 centimeters, 2 centimeters, 2.5, 3. Fantastic. It's continuous. So a lot of you guys are saying C, but by C, I hope you mean continuous and not categoric. So the tissue is continuous. Okay. What about the distance which the X-ray penetrates? If we just go back to their graph so you can see it clearly, can you see these are all numbers that are following a continuous scale? These are all numbers following a continuous scale. So both of these variables are continuous. Okay, they can follow a range. It's not like it can only be this or this or this. And this is why when you have got two continuous variables, you must use a line graph. Okay, if for example your experiment was slightly different and you had a categoric variable, then you would use a bar graph. Okay, so say for example, if you had like a number of people, okay, that number of people here is a continuous variable, but your category is your eye color. So this number of people are blue, this number of people have got green eyes, and this number of people have got brown eyes. Okay, these are fixed categories. Eye color is not on a continuous scale, it is a category. So that's when you use a bar chart. Okay, and this is when you use a line graph. So hopefully that makes sense. And this is very valuable knowledge, not just for physics, but even in maths, in any science experiment that you do, you will see questions like this. So I think that was a good one to do. Great, so the correct answer here is both variables are continuous. What happens to X-rays when they enter a bone? What do you think? Okay, so some people saying they are reflected, they go through, they absorb. So basically, I'll show you guys a picture of an X-ray, but whenever you look at an X-ray, like for example, of let's say somebody's knee, this is their knee here, and this is their foot. On the X-ray, you see the whole bony bit and it's white, isn't it? Everything else around it appears to be black, and that is because the X-rays, when they enter a bone, they are absorbed. The bone absorbs the X-rays, and that's why you can see it, because you absorb the X-ray and it appears white. The X-rays, if you put your X-ray like through your tummy or like through your skin, it goes straight through and it is just transmitted through. And that's why on the X-ray you can't see your nails, you can't see like your skin or any internal organs. You can just see bone. So X-rays only show us bone. Okay, that's why it's very useful. Like if you have an injury, then you get an X-ray done to see like if you had a fracture or like you damaged your bones. That's the main use of X-rays, because X-rays are absorbed by bone, but soft tissue like your skin, it will go right through it. Okay, your skin doesn't absorb the X-ray, it just passes through. Okay, and just one more question. So how are images formed electronically in a modern X-ray machine? So let's use our process of elimination to work this one out. Do we think it is with an oscilloscope, firstly? Exactly. It's not the oscilloscope, right? Because if you remember, the oscilloscope is what we use to detect the sound waves when we're doing experiments to measure wave frequency. Okay, we talked about this in the morning. So we're left with a charge coupled device and a photographic film. So photographic film is actually what we used to use many, many years ago. We used to take like a picture and it would print out on a film, just like how, you know, like with those really old school cameras, that you print out a film and you get a whole picture of it. In some developing countries, they still use photographic film. So like if you get an X-ray abroad, sometimes they'll give you like a big film to take home. But in modern X-ray machines, we use something called a charge coupled device, and that is what we used for to form the image electronically, because this connects it to a computer and we see the image on a screen. We don't have to print it out on that photo paper. So I just want to go back because I haven't actually covered this. I just thought we could do some questions before we get a bit bored. So let's just go through X-rays. So where were we? Yeah, so talking about the ultraviolet rays. So remember there was a question which said the security tags. So that is using ultraviolet rays. So UV waves are emitted by hot objects. Some substances can absorb the energy from UV radiation and then emit the energy as visible light. And that is what we call fluorescence. That's how we can see those tags. So some types of energy efficient lamps work by producing UV radiation. And you can see that over here. So when electricity passes through a gas in the lamp, reactions occur and UV radiation is emitted. And the UV radiation is absorbed by a chemical which covers the inside of the glass. And the chemical basically fluoresces, it gives off that fluorescent energy and visible light is emitted. So this is, for example, when you've got these notes, like a lot of people can print fake notes, and the only way we can check is if the notes are real is because they've got a hologram, and that hologram is only visible under UV light. Okay, and what we do is you shine the light on it, and if it is a real note, you will see that like a hologram appears, and that is how you know that this is a real note. And you can try this next time. If you take your note, if you hold it up in bright sunlight, you will see that there is some like holographic image of the Queen appearing, even on the UK notes. So that is basically using the property of UV light. And it's not just in like in banknotes or in the security tags, it's also used in solving crimes and also in some scans as well. So does anyone know what this scan here is of? It's a part of the body. Excellent. So this is actually a brain scan. This is an MRI scan of the brain, and what you can see is that all of this area is normal, and this bit has lit up in red. Does anyone know what this could be? Like, why is there a red bit in the middle? Excellent. Yeah. So this is probably a tumor. So it's an uncontrolled growth. It shouldn't be there. But it is there, unfortunately, and we can use the ultraviolet light because it has basically lit up in a different color. That's the only way we know it's there. If everything was the same color, you wouldn't be able to tell, because can you see there's loads of blobs everywhere, but it's because this one is a different color that we know it's not part of the normal brain. Okay, so yeah, in an X-ray photograph, bones, teeth, and diseased tissues stand out because they absorb the X-rays. It's mainly the bones that you can see, and you can see teeth. And lastly, we have got gamma rays. So gamma rays are a penetrating radiation which can cause damage to body tissue. Sometimes this is useful. So gamma rays, it's a bit of a, it works both ways. So gamma rays, because they're so powerful, they can cause cancer and they can kill cells. But if a person already has cancer, we want to get rid of those cells and we want to kill those cancer cells. So what we do is we give them gamma rays to get rid of it. So it's kind of, can you see how it's like a bit of a sticky situation? Because if somebody's exposed to gamma rays, they can actually get cancer. But once they get it, we give them more gamma rays so that we can kill off those cancer cells. So sometimes this is useful. So for example, gamma rays are used in radiotherapy, which you may have heard of before. This is radiotherapy going on in action. So these are machines which are delivering very powerful gamma rays. This is the symbol for gamma. It looks like a Y. And they are just all from different directions. They all put gamma radiation localized on that tumor. Okay, what do you think would happen if these gamma rays were not focused on the tumor and they would just hit over the body? Do you think that would be a problem? Exactly, it would kill all the body cells, okay, because gamma rays are very powerful. So the way that they focus the rays, it has to be really, really precise and really focused. So can you see how it doesn't matter where the machine is, the only way it's trying to reach is to reach the tumor, okay, from all areas. Even if it goes like slightly over here, you will literally destroy the person's leg or like give them a brain tumor or something. So you have to be really careful with the gamma rays. Okay, and just one last question before we move on to our quiz. So well done, guys. We're nearly there, only 15 minutes left. So figure 2 shows two students measuring the speed of sound in air. One student bangs two bricks together. The sound wave produced is reflected from the wall and travels back to the students. Describe how they can determine the speed of sound. So we saw this experiment in the morning. I think we didn't think much of it, but here it is now in the exam papers. So let's try and remember what we can do. So we've got one lady here and she's banging the bricks, and the other guy has got a stopwatch. How can they determine the speed of sound? So I'll give you guys just a minute to think about it and we can brainstorm ideas together. Now, this is a describe question, and this question is assessing your ability to conduct an experiment. Okay, so in your exams, like towards the end of the paper, they will always give like some really weird experiment question. And from experience, even if you've never done the experiment, there are always fixed things which you guys can write down and you will still get a few marks. Okay, so those are some of the things which I'm going to be telling you guys about. Now, let's just talk about it. They've basically given you everything. They're telling us that the sound wave is reflected from the wall and then it goes back to the students. Okay, so how can they determine the speed of sound? What's the first thing that they need to do to work out speed of sound? What's my equation for speed of sound? In an experiment like this, how can I calculate speed? So if you guys remember from this morning, we said that when you're doing an experiment like this, your speed is always equal to your distance traveled over your time, okay? Where this will be the distance traveled from it to go to the wall to the back, and he's measuring the time taken, okay? So he's measuring how long does it take once she hits the bricks for the sound to travel back. So the first thing that you want to say is measure the distance between the student with the bricks and the wall. Yeah, that's the first thing you want to do. You want to measure the distance. If we're doing an experiment, how do we measure the distance? What do we need to use? Because there is a mark for just saying that. What do you guys use to measure distance? So what piece of equipment? Okay, so some of you saying ruler. So a ruler is about 10 centimeters or 20 centimeters. So do you guys really think that you can use your ruler to put this here? Good try. Exactly, the ruler is too small, isn't it? So you just say using a tape measure. Okay, you have to use a proper tape measure because if you use your ruler, it's not going to be accurate. If you imagine your ruler is like literally this big, so you can't keep holding the ruler everywhere. Okay, so we use a tape measure. Okay, so that is we measure our distance. Then we need to measure the time. Okay, so then what we can say is we measure the time taken. Measure the time taken from banging the bricks to the echo. Okay, so you see how long does it take from banging the bricks to the echo. Okay, and they've already said that he's got a stopwatch. Okay, so you're not going to get a mark for saying using a stopwatch because he's already got one. Then you can say speed is equal to distance over time. Okay, because that is your equation that we have to use to then plug in the value. So you measure the distance, you measure the time. Okay, so these are already your 4 marks. Then there are things that you can say, like generic things in any experiment. So what other things can you do to help improve the reliability of your experiment? Do you think they should just do this once? Exactly. So repeat multiple times, because this is just one person, okay? Like you're just relying on this guy's hearing. I mean, he might not even be paying attention. He might even not even hear the echo. He might be not concentrating, playing on his phone. There are many factors, okay? So this is why, because there is human error, he needs to do it multiple times to get a reliable reading, okay? When you repeat something, you increase the reliability. You repeat it multiple times and you remove anomalies. Okay, does anyone know what we mean by the term anomalies? An anomaly is something which does not fit in with your data. So it might be like 15 seconds, 20 seconds, 18 seconds, and then all of a sudden he's got 5 minutes. Okay. Now obviously something went wrong. He wasn't paying attention there. Okay. So anomaly is something that does not fit in with the pattern, and you have to discard it because otherwise your whole experiment will be messed up. So you remove any anomalies that, based on what mistake you might make, and then you calculate a mean. Okay, you calculate the average. So you add up all your results and you divide it by 3. So you probably get something like 18 or 18.5, and you know that that is on average this time taken for the speed of this sound. Okay, so these 3 points are things you can say, like in most experiments, you know, repeat it, remove anomalies, and calculate your average. Okay, so those are just the answers over here. Does anyone have any questions on this? Okay, well done, guys. We have finished. It's now time for the last quiz of today. So well done. Okay, so if you guys log in with something that you have learnt today, and it can't be wavelength or frequency, that is all I'm seeing. Okay, I think we will get started. If you haven't logged on, the pin is at the bottom. Okay, true or false? All electromagnetic waves travel at the same speed. Okay, guys, so this is actually true. So this is a key point. So I just want to go back to this so that you guys are all clear. So in the beginning, we talked about electromagnetic waves, okay? And remember, we said these are the 5 key points about them. All electromagnetic waves travel at the same speed, okay? And remember, I said this is a number you need to know, 3 times 10 to the 8. So that is true. So well done if you said true. How many types of electromagnetic waves exist? Excellent, we have got 7, and you should have been able to see it in the diagram. All electromagnetic waves travel at how many kilometers per second? Fantastic, so we did just see that, it was 300,000. Fantastic, that is very true. Okay, seismic waves is in the lead. What type of electromagnetic waves causes sunburn? Okay, which one was it? So it is UV radiation which causes sunburn. UV radiation comes from the sun, okay? It's not visible light that will give you a burn. All waves can be reflected. So this is true. All waves, they do have the possibility of being reflected. It just depends which medium they are in. Okay, if you go from glass to air or water to air, they might become refracted, but they have the potential to be reflected. Which of the following statements about EM waves is correct? Fantastic. So this was one of our key facts. All EM waves travel through a vacuum at the same speed. That is 300,000 kilometers per second. Which of these EM waves is the most damaging to human tissue? Is it UV, X-ray, or gamma? Super, it is gamma rays. Okay, UV is the least damaging out of those three. Okay, and last question. Why are waves important? Okay, so this is all of those things. So if we didn't have waves, we wouldn't even have this computer in front of us, cell phones, radios. Okay, we wouldn't be able to hear or see things because we use sound waves and we use light waves, and there would be no heat because we use infrared waves. So basically, waves are probably the most important thing to exist. Fantastic. Seismic waves took the lead. So well done, you guys. A lot of you got nearly 4 marks. I'm really, really happy with that. Okay, so does anyone have any questions on what we have covered today or anything that you guys didn't understand? If you guys don't have any questions, it's just coming up to 3 o'clock, so I think we will stop there. So thank you guys all for joining me today for this wave session. I really love teaching it. I hope you guys took something away. We will be sending out lecture notes which summarize everything, so please read them, as well as the recording, the handouts, and the mark schemes if you haven't done most of the questions yet. But otherwise, it's getting a bit sunny, so I hope you guys enjoy the rest of your Sunday.